Are you completely back up, Kathy?
Yes. Let's just hope it stays that way.
Well, let's see, can we make Talinda the co-host? Because I guess if your computer did go down, as long as we had another co-host online, the live streaming should not end. Because the event will still, I think it's set up so that if you still have a co-host there,
Yes.
the event still goes on. So that way, if something happened and you dropped off, then as long as Talinda is on there, everything will stay live.
Why is it not allowing me?
Okay, so the live streaming looks like it's working, which is great. I'm gonna get that up on the webpage then.
Okay, so Justin, when I look at yours, it lets me make you a presenter. But it does not let me make Talinda a presenter. And it doesn't let me make anybody a co-host. And I've been able to do that before. Maybe it has something to do with the live being turned on.
It shouldn't. I mean, I don't see those controls on my end, so I'm not sure what is going on.
Yeah, it's not letting me make her a presenter. That's a problem. Linda, can you try signing out and logging back in?
Certainly.
Oh, that's really weird.
Okay, I'm back in. Now I used the link that you sent out this morning to the team. Is that the right link?
Yes.
Wait, you can't make me presenter, but I can still show my slides?
That's right. You did show your slide. You are showing your slide. Okay, so at least I've got that. Okay, so we don't have to worry about it then. But I can't make somebody a co-host. It just says make presenter. And for some weird reason, maybe it automatically made you presenter because you just started sharing your slide, and that's why I can't see it.
Yeah, that could be it. And co-host, I don't I think we had this issue the other day. I noticed I think we can't actually assign co-hosts because we only have one host license. But didn't we kind of have this the other day where we tried to do that and I think it didn't work as well? I'm
Right.
thinking of something different. I can't remember. I mean, we did it yesterday when I logged back in as you, and then I was the co-host. I mean, I guess that's an option, as I could log in as you and make me the co-host, and then if your computer went down, I'm still there.
Oh, we've got some people logging in.
Yeah, welcome everybody. If you're just joining us, we're still getting set up here. Kathy, I think I'm going to log out as you, or log back in as you, and just as a backup.
Okay.
Okay, Kathy, you are so there's two profiles now. You're the official host, and this other account that I'm logged in as co-host. That way, if anything happens, I'll still have mine up.
Okay.
Okay, well, I'm going to go live with the live stream then.
Yep, go ahead.
Good luck to you.
Thank you. Oh, hi, Brent.
Hi, hope everything goes well.
Thank you. We had a few technical glitches. But we're doing good now. And you can see the slides, right? That I'm presenting. Good.
Everything looks good. Yeah, I can see everything.
Great.
I'm going to go on mute and so on to save the bandwidth.
Yeah, and take your screen off, video off also. Perfect. Thank you, everyone, for joining us. We will be kicking this off right at 1 o'clock, so stand by. I see more folks are coming in to the symposium. The agenda has been posted on the UDMC website, which is utah.defense.mfg.org under events. And for meeting information, we'll take a 15-minute break at around 3:20. I'm Talinda Larson. I'm going to be the moderator. If you're on WebEx, if you would please turn off your video and mute yourself to save bandwidth. We'll be able to ask questions through both the YouTube channel and also on WebEx through chat. So now it is 1 o'clock Mountain Time here in Utah, and let's kick off our first Defense Manufacturing Research Symposium. I am Dr. Talinda Larson. I have the privilege of being Executive Director for the Utah Advanced Materials and Advanced Manufacturing Initiative. And I will be your moderator. So I'm going to screen right now so you can see me. This symposium is being held by the Utah Defense Manufacturing Community Program, which is under the Defense Manufacturing Community Support Program, which is administered by the Office of Local Defense Community Cooperation. I don't see myself as the screen in the. Let me just ask for a little technical feedback. Justin, am I projecting on the YouTube stream?
Yes, you're projecting on the YouTube stream.
Very good. Thank you. As you know, we have two ways of participating in the symposium. Our preferred way is if you would join us through the YouTube, because we have more than 350 attendees. But we understand that some folks cannot do that due to restrictions either on the military or other reasons, and we did provide the WebEx. So back to this symposium is being held by the Utah Defense Manufacturing Community Program, which is under the Defense Manufacturing Support Program, administered by the Office of Local Defense Community Cooperation. The Utah Defense Manufacturing Community has more than 70 consortium partners, and we have 4 pillars: workforce, supply chain, research, and small business. The Utah Governor's Office of Economic Development is the lead on these programs in this grant, and Utah's Advanced Materials and Manufacturing Initiative serves as the administrator. Today's symposium is under the research pillar, and it's designed to better align research initiatives with the defense industry's requirements for research related to supporting defense manufacturing. The agenda with the speakers' bios, as I had mentioned earlier, can be found on the UMDC website under events. Today's presentations some have been pre-recorded, while others will be live. What wonders we are living in this new world of virtual conferences where you can have some pre-recorded and some live. So let's get started now with our first speaker. And this presentation is a recorded presentation. Unfortunately, we had a scheduling conflict, but we were able to last minute be able to bring in our first speaker and have her pre-recorded yesterday, so she didn't have to try and do the presentation in a airport setting. But Angie Timofeychuk, who is Deputy Assistant Secretary of the Air Force for Logistics and Product Support, will be joining us at the end of the pre-recorded presentation to be available to answer questions and to be able to participate live at the end. So now our next presentation will be run, and I guess I have to stop sharing my screen. And there we go, ready for the presentation to be run. We don't have sound.
Got it.
Welcome, everyone. And here we are with our first speaker of the day, an excellent presentation to really kick off and set the stage for all the things that we're going to be discussing the rest of this afternoon. Pleased to have with us Angie Timofeychuk, who is a member of the Senior Executive Service, and she serves as Deputy Assistant Secretary of the Air Force for Acquisition. She has a very distinguished career, and you can find that in the program. But we're pleased to claim her as her time in Utah with Hill Air Force Base. And then she was part of the original founding of UAMI. So thank you for your service to the United States, and thank you for your service to UAMI. I will run your slides maybe while I'm getting those set up if you want to share a few introductory words.
Yes, thank you to Linda. And as you mentioned, I still claim Utah heritage. I didn't grow up there, but I have some very strong roots at both Hill Air Force Base and UAMI itself. In fact, during a couple of years outside of the Air Force, I had the direct privilege of working with through UAMI. And so I'm looking at the RSVP list, and lots of familiar friends and some people close enough to call family. So it is my honor to be here today and to share with you some thoughts that are hopefully helpful to the consistency of UAMI in terms of how we're approaching acquisition different within the Air Force. And you see my subtitle there and how you can better participate. And that I put a subtitle. I'm not going to spend a lot of time on that, just one slide, but I'm hoping that through the comments, you start seeing how things are changing and how you might be able to better and be a stronger participant in Air Force acquisition. I will say that my slides are built along the Air Force acquiring things, capabilities. You'll hear later on in the program some of the more R&D type activities. My friend Tim Bunning and Tom Lockhart and Don Russell talking about more on the R&D side. So a little bit of what I'll talk about applies to that side, but I'm talking about the acquiring goods and services and capabilities. So my first chart here is meant to capture the essence of the Air Force's path on what we call going digital, a concerted campaign to change culture, processes, and products. And the premise behind the digital campaign is what the Air Force our capability, quality, and effectiveness remains superior. The time it takes us to field new capabilities is our greatest hindrance to maintaining dominance. So we need to deliver capabilities at ever increasing speed and efficiency by designing, sustaining, modernizing them in an integrated digital environment. So the chart, if you look at it, it's going to serve as my outline. So I'll just briefly discuss it. On the bottom, on the right, we're talking about the digital trinity. I'll give you an introduction to what we mean by that. It is the enabling activity that enables digital acquisition, and it enables our connected environment, and you'll hear the term digital thread. The second piece up on the right is the commercial, the concept of leveraging the huge investment that industry and investors have placed in technology that the government used to be the lead on. Now it is flipped, and can we leverage and take advantage of those dollars and applying them into the DoD, and in this case, the Air Force. The next piece up there is really the holy grail, the end product of what we're building up to, and that's called the E-Series. And the example program is Next Generation Air Defense, but I'll kind of explain what that is versus what our current legacy portfolio looks like. And then, of course, on the bottom left is really what we're talking about. It's that digital acquisition. So how do we pull all these things together and acquire things differently? So I neglected to talk about the top on the left-hand side. Innovation is the battlefield. Innovation has changed the battlefield. If we're talking about warfare, that has been the case all along. But in this case, our battlefield is how we acquire things. And that brings a whole new light to the discussion, right? So we're going to innovate on our processes that turn around into our products. So, and the piece that I won't necessarily talk on today is the culture of our workforce and the talent that it's going to take to implement the things that we're going to talk about. That is a very concerted effort within the Air Force to bring, like my position is logistics and product support. How do we as lifecycle logisticians embrace the digital environment, embrace digital engineering as it applies to our career field, and how we sustain weapon systems as they're fielded and operated. So if we go to the next chart, I'm not going to spend a lot of time on this one because I know Colonel Diller is your next speaker with AFWorks. But I did steal one of his charts from a previous presentation that he gave, and it is just to show you the concept that one of our who leveraging the commercial investment is AFWorks. And I highlight the red circles and the arrows on the chart. That is a paradigm shift to the way we used to acquire things. So we used to set out the rigid requirements, and you send out an RFP. It'd take you months and years to put that together, months and years to evaluate it, and then we'd neck it down to a specific user, a specific use case within the Air Force. Now we're doing that differently. We're saying, hey, industry, we know you've developed goods and services. Tell us what they are and let us figure out if they apply, if we can apply them to a capability need within the Air Force. So you see a lot of TBDs. We really don't know what application we're going to apply to, and we really don't know who that end user is, but it's a capability worth pursuing further. And so that's one example, AFWorks. And again, you'll hear Nathan talk about that, and I'll go to the next chart. And so the other who that we're really talking about is the Rapid Sustainment Office. So I noted that I actually forgot to spell out the acronym on my chart, RSO, Rapid Sustainment Office. It is about a little over 2 years in the makings, and it's recently been stood up as a program executive office within the Air Force, and the RSO PEO, and it is fundamentally different than any other PEO that we have within the Air Force. And I'll point out two things on that chart in specific that make it different. The first is, if you read the objective, increase readiness by identifying, applying, and scaling technology. So I'll talk about that in a minute. And two, the board of directors. You see those faces on the bottom. Those spaces comprise the 3- and 4-star general officer level positions within the Air Force that all cover the senior leadership positions in any capability that we acquire or sustain. So it enables the Rapid Sustainment Office to come in and apply technologies across the Air Force portfolio. I don't think it would be a stretch that many in the audience are aware that the problems we have porting technology and solutions across weapon systems with the Air Force. It's a huge hurdle in the process, sometimes on purpose. But if you apply to one weapon system, you apply to one weapon system, and it's just starting from scratch as we go along. The RSO is working on helping to alleviate that issue by bringing all the right players to the table. You see the bottom right hand of the chart, that little picture is meant to represent how they do this. It starts with a broad brush, identify technologies. Similar to what AFWorks is, they say, I want to develop the technology. You see in the black some of the areas they focus on, robotics. Show me what robotics capabilities you have, industry, and I'll figure out how I need the next funnel down is apply. How can I apply your technology to a need within the Air Force? And so we're working through the identify, apply, and then finally scale. What are those high return on investment technologies out there that we've identified, we've applied successfully to one, maybe multiple platforms, and now we really, really need to push it over the end goal and scale it across our fleets. So the two that are in that phase right now are CBM Plus, capability-based maintenance, and the second is additive manufacturing. So we'll advanced manufacturing, depending on how you how you look at it. So there are two technologies. So if we think about cold spray, could be one of them. Additively manufactured parts and how we grow that marketplace, both from tech data availability and a vendor availability. So those are the two areas that we're focused in on more. You see on the slide, there's several other focus areas. In interest of time, I'm not going to go into detail on those. I did not put their website on. There's another mistake. It's Air Force RSO, all acronyms, afrso.com. So again, leaning outside of that .gov environment and really opening up the aperture to commercial entities in order to communicate better. So if we go to the next slide. Now I'm going to go into that what, and that was that top block that said E-Series. So let me step back a minute and talk about the green bubble, which is the conventional programs. Those are the programs that are in that multi-decade development process of the old system, acquiring things over multi-years. So you think F-35, yeah, it's still a little bit in development, but the capabilities being filled, and it's been in development for many, many years. Then on the right, in the blue bubble, we have what we call the E programs. Those are the things that are going through some kind of digital acquisition process. So we think about the T7, our new trainer. It's being developed in a digital engineering environment, and they're really digitizing their processes. And we actually have an Air Force instruction that allows the E designator to go on to programs that meet certain criteria. So we have an ET7 programs. That means it's being digitally designed and developed, this new trainer system. So even so much to go and call them out is different, so that across the board, we can identify which programs will fall into this construct that I'm describing here today. Within the E programs designation, there's something called E-Series, and that is very specific for rapid capability development. When we think about the old 100 series aircraft development, rapidly fielding a capability, but in this case, create before you aviate. So we're not risking or losing life or treasured aircraft. We are doing this all virtually. So the first program that we're designated as an E-Series is called the Next Generation Air Dominance Program, NGAD. I'm not going to go into a lot of detail. A lot of that I can't in this forum anyway, but I will show you a video here coming up that'll give you a good idea of what that means. Finally, on this chart, I want to show you the middle section there, which is the overlap in the Venn diagram. And I'll touch briefly at the end. We'll touch on the end because that's my sweet spot. My sweet spot is how does all these digital tools, how does that apply on a legacy platform when you don't necessarily have all those tools from day one? So we'll talk more about that in a little bit. Okay, go to the next slide. So I'll talk while it's going. So this gives you an idea of what we mean when we talk about modular open system architecture. And we're not just talking software. Typically, the concept of this modular open system architecture, people automatically think software, but we're talking about hardware in the loop. This is a borrowed 10-second clip of a speech my former boss made at an Air Force Association conference. You see the reference to it at the bottom if you want to see the whole presentation, because it really will get you excited about where the Air Force is going with acquisition. No sound on purpose, because again, I stole this from his presentation, but really what you see here demonstrated is, no kidding, a plug and play concept from a hardware and a payload perspective. So if you're thinking about swapping out nose cones on a flight line, where your mind goes is a standards architecture that allows that to happen. And once you have a common standard, you're no longer tied to a specific vendor, and you can compete that. So we're opening up to different vendors that can provide that capability. You can also see what this could mean to maintenance too. So you're right there at Hill next to the Ogden Air Logistics Complex. What does this mean for maintenance? So we need to modernize our depots too. Are we going to be doing large airframe structural work 20, 30 years down the line? To be determined. But there's lots of work left to do in aligning that enterprise. But this just gives you that visual concept of what we talk about by plug and play hardware. Okay, the next slide. Okay, so the digital thread. This is no kidding, the picture of what we speak about when we talk, we corporately speak about for that digital thread. Okay, cool. There's new programs and they talk about if you're designing it from a blank sheet, yes, all those parts and pieces that are on that thread, they exist, period. If you know me, that part at the end that talks about logistics and sustainment, and then it goes off and it says operations, maintenance, modernization, replacement, disposal. At least two, if not three of them, they lead you to circle back. So if you hit forward to Linda, really, it's a continual development process, right? So we don't just go through the design process once, send it out in the field, never have to look at it again. You're in sustainment. You're dealing with obsolescence. You're dealing with modernization. You're dealing with whatever issue comes up in operations that you need to go back to the table and redesign. You're going to loop back. So really, we talk about that Venn diagram and the legacy versus the E programs. This is what it gets at, and this is what I call digitizing sustainment. So I stole this example. I don't know if there's anybody from the A10 in the program office or programs at Hill, but I took some information from a briefing that they gave my former boss, Will Roper, on how they're taking digital tools and the digital acquisition environment and applying it back to the legacy system. So when you think about this 1960, 70 design on the A10, and you look at the 2D drawings, which probably were state of the art at the time, document-based tech manuals, very manually intensive to keep up to date, to keep configuration managed, to provide updates, just all the data that existed on individual engineers and logisticians, equipment managers, you name it, as they were working things on their particular laptop. No thread, no digital thread connecting all that activity together to where they are now in the A10. And it was really taken off by the CAD modeling that was done with the A10 rewing. So even one of the E program designations is the A10 rewing. So it was an E designation associated with that. They really took off and allowed the program to exponentially delve into digitizing sustainment. So again, this came from a briefing that they gave to my boss, and he asked him a question. He goes, okay, you have the wings, you've done a lot more work on actually the model development, reverse engineering, how far are you away from being able to say, I have a digitally rendered model of this system, at least structurally, that I could pass over to a manufacturer and be able to remanufacture an A10? And I kind of stood back for a minute. I'm like, wow, that's an interesting question. And I was even more intrigued by the response, which essentially, bottom line was, we're not that far off. So can you imagine so that we'd be able to recreate a system, again, a structural system, the structures only, that we could pass over to a new manufacturer and say, I need a new A10, go give me that. And be able to do it. That is mind-boggling. And so not only are they doing it on the airframe, the system itself, but when you think about pulling their processes into the modern digital world too, they're creating that digital thread themselves. you can actually look at a maintenance assistant request, tie it to a specific location on a specific airframe, look at activities going around and be able to tie a diagnosis, an NDI to a location, being able to data mine across the fleet for common issues. And it's just, you can imagine how much more efficient and effective the maintenance and the sustainment is. And it gets at readiness, and that's the real return, providing ready aircraft to meet our national defense needs through digitizing sustainment. I like that word, I'm gonna say it a lot. Now, you may be saying that the A-10 is a bit different because there is no OEM. Fair. Next chart, please. So I wanted to highlight another effort that we have ongoing, and that's to reverse engineer a B-1 structure. So they have an OEM, right? The National Institute for Aviation Research, NIAR, at Kansas State University. I actually met them when I worked for UAMI at the time. The executive director came to me and he wanted to know how they can leverage their innovative capabilities and expertise in reverse engineering and how we could use it within the Air Force. And so we talked about it a little bit, and we identified a significant return on investment project towards addressing readiness issues with the B-1. We had discussions, and this is corporate, Air Force, had discussions with the OEM on the need for structural loads data in an as-flown airframe. Somewhere between it can't be done, a price tag we couldn't stomach, a willing, capable partner, and I'm sure a bunch of other what ifs in there, that we decided we had an alternative now. And the B-1 program office identified an appropriate aircraft at AMARG at the Air Force's Boneyard, extracted it from AMARG, Tucson, Arizona, trucked it to Kansas, and the airframe delivered in May, kicking off the project. Every part, bolt fastener, will be meticulously removed, cleaned, inspected, scanned, and virtually reassembled to create this digital twin. And you can see on the chart, this was just updated not too many weeks ago for a different presentation. Their part estimate went from about 20,000 originally to about 75,000 parts in total. It's the airframe, right wing from one aircraft, the left wing from another aircraft, and piecing them all together. So all this to say that if the structural data doesn't exist because the OEM no longer exists, or we didn't procure the data, or the price tag is unrealistic, or whatever, we now have options. And if you can create an as maintained and as operated digital twin, we can predict remaining life or needed repairs, and you can proactively work obsolescence, long lead, and never before procured repair items. And we can open it to new vendors. So we own the tech data. We can actually do what we have wanted to do, and that's to go from no or single or low number of vendors to opening it up. This is really groundbreaking. And it's not just the Air Force. The Army simultaneously has a Black Hawk helicopter at NIAR with the specific purpose of generating government-owned tech data to get after supply issues, as well as improving repair time on components. This is digitizing sustainment. Okay, next chart. Okay, this is really not my forte, but here I'm talking to Utah, and I will not leave without touting on the 309 Software Engineering Group and the efforts that they've taken. So when we talk about cloud-based agile software development, they are it. So just tremendous capability. We used to call them the software maintenance groups because all they did was maintenance. This so far was always so far from the truth, but this in particular is something notable. So there's a technology called Kubernetes out there, and you can think about it as a secure container of software that can be inserted and transmitted securely. That can provide rapid software updating and no longer have to wait a 1 or a 2 year to pull all these different capabilities together and then upload the new software package. No, we're doing it incrementally. So it's a rapid delivery of capability onto the platform. So the 309 SWAG, through their SonarCube effort, they were the first to demonstrate the ability to do this on the F-16. So since then, the Air Force has successfully demonstrated on U-2 and on the U-2 and the T-38. Maybe another that I haven't caught yet, but that is tremendous activity going on at the work at our SWAGs, and we hope to continue to support and endorse their activities and endorse their ski camp activities, and opening the aperture for industry and academia to participate with them in software development, and also from a STEM outreach and workforce development perspective. So next chart. So this is where I said, how can you participate? And again, keeping it at a very high level. This is motherhood and apple pie if you think about it, but think about that standard-based approach, and again, how differently that will morph the way we acquire things. And most importantly, that standards-based architecture development is currently ongoing. So there's a group headquartered out of Wright Pat that's doing that work right now, bringing in industry, bringing in academia to define the standards moving forward. So it's activity to definitely be aware of now. The second one is help us help you, just like you're going to hear from, I think you're going to hear out of Colonel Diller.
As you know, we have two ways of participating in the
symposium.
symposium.
Trying to do, all the spark tanks are trying to do is, we don't know what we don't know. And so the next bullet, as you're aware of webinars, challenges, etc., to pull all these different capabilities together, bring your thoughts, bring your products to the table, and finally, that last bullet there, try again, that will morph the way we acquire things. That I've made at least one thing clear, and that is how much the Air Force has pivoted in terms of the way we are acquiring things moving forward. And we're trying to be more inclusive. We're trying to get away from the we know better. Only give us what we ask for. Don't give us a different kind of coolant, because it is the current coolant used out there per requirement. Only give me what you want. So we're really moving, 180 degrees away from there. Try again. I finally throw up here, the last is just a plug for the Rapid Sustainment Office, just another example of how we're doing things different. We have a commercial solutions offering out there. Give me your ideas. Tell me what product you have. Again, not R&D specifically, but a product you have that can provide capability to the Air Force so that they're aware and can work on that competitive contract vehicle out there. There is a link on the bottom to that CSO on sam.gov if you don't have it. With that, sorry, I think I went maybe over.
Don't worry about it. Definitely don't worry. Excellent presentation. Thank you so much. And now for those of you attending, we're going to switch from this recorded presentation to live questions, and Andy will be available to take your questions. I will thank you properly then.
All right.
Okay, so now this is to Linda Larson back with you, and we are going to have a shout out to Angie Timofeychuk. Angie, are you on the line? Or we may need you to unmute yourself. She was anticipating calling in, and give her a second. I can't tell by phone number what her phone number is. Angie, have you dialed in? You love the technology, but sometimes these things just don't really work so well.
Angie, if you can hear me, try *6 to unmute yourself.
Can you hear me now?
Yes, we can. Fabulous.
I'm sitting here trying to talk. Hello to Linda. Hello, UAMI.
Thank you again. We're broadcasting two ways, through WebEx and through a YouTube link, which again, I apologize for those of you who had the wrong link at the very beginning. All of these proceedings will be available, but we do have Angie live now. So Kathy, do we have any questions for Angie coming in?
We do not have any questions in chat at this time. Except if anyone wants to enter their questions in chat, please.
I got a question.
Is that you, George?
That's me.
Hey, George. Say
Hi,
hi to
George.
hi, Angie. Hey, so you're looking at reverse engineering a lot of things and a lot of hardware and a lot of software and a lot of things that eventually you want to go 3D print. I just had to put that plug in there. As you reverse engineer these things, are you engineering them to the point where you can take advantage of the advances in machining and the advances in printing and the advances in manufacturing methods and the advances particularly in materials against not only the weaponry, but countermeasures against future weaponry and things like that, that you can both reverse engineer and modernize at the same time?
I'd say that depends on the particular project. Yes, there are activities that are looking to improve based on reverse engineering to improve. There are others that are simply looking for a new vendor. So it just, my answer is it depends, but absolutely we're interested in new modernized technology and capability when the situation arises.
Good.
other questions. Feel free to unmute yourself and ask a question. Identify yourself. Oh, we can't let her off the hook that easy.
Oh, come on.
Corianne, I see Corianne Edwards is on with GoEd. Corianne, do you have any questions or shout outs to Angie?
Hi, Corianne.
Hi, Angie. Just can't have to take this opportunity to say hi to you. So thank you for participating. A lot of the great work that UAMI is doing today, we can thank Angie for so much of the groundwork and foundation for that. So thank you for that. One of the questions I do have for you is, I mean, knowing UAMI and knowing this community and audience that's on the phone, do you think that we should be, do you think there's a partnership with NIAR? Any recommendations for maybe what NIAR is doing and some synergies that Utah might have that we should be looking at? I know that's kind of a out there question, but.
No, it's okay. I can tell you that the work with NIAR and the Air Force has expanded well beyond B1. In fact, we got a new project kicking off with the F-16. That's very close to home there in Utah. So I think at one point, I know UAMI and the University of Utah had started a discussion on growing that relationship. I think along those lines would probably continue, and that was along the digital thread concept and helping to tie all this information together, and that was to include the models and simulations that were being accomplished through the University of Utah, and tying that into, I'll use air quotes, condition-based maintenance. So how things fail, why they fail, and to George's comment earlier, can we improve things as we're going along so that we can accommodate failure modes. So yes, I think there's conversations still to be had. I know NIAR is open to it. I know they're.
So one question based upon what Corianne just said then. This is George again. What, if anything, can you say about the possibilities of the sustainment center being set up in Utah?
Repeat the question, you cut out.
what, if anything, can you say about the possibilities of a sustainment center being set up in Utah?
So I think I recall the conversation is more because I think in terms of the Air Force Sustainment Center, and they are at Utah, but you're talking about like a sustainment center of excellence kind of thing.
Well, growing it bigger, because if we get a big sustainment center here, then we have the opportunity to indeed not open up the same opportunity that NIAR opened up in 20 years ago, but to be able to open up a sustainment and excellence opportunity where the improvements that you talk about or the cloning you talk about, whichever, can actually happen in Utah.
So I think I'm going to punt that question. I think you should ask that one of both Tim Bunning and John Russell later on in the day. They are the community that represents the manufacturing institutes, which I think would be the program that would sponsor that kind of activity.
Good point.
I see Brent, who is the UAMI chief scientist. Brent, you had a question?
Yes. Hi, Angie. It's nice to hear your talk.
Hi, Brent.
I'd like to ask you, one of the problems that we are encountering is very small shops, maybe 10 people, are having trouble getting qualified to supply the Air Force. Do you see any method that can help them, any changes in the qualification system that would be either less expensive or less time consuming that can help small shops begin to be suppliers?
So two different sides to that answer. One is I seem to recall a mentoring program that large companies would sponsor small companies to mentor them through that process. That's for traditional manufacturing. I know that there are efforts within the Air Force and larger within the DoD to help level set in terms of additive manufacturing, creating standards. So it takes a different flair from there, but no particular program that I'm aware of that I could point you to right now, though.
Okay, thank you.
Hey, Angie, this is Julie Fisher. Nice to hear your presentation, and thank you for such a great job. I have a quick question for you. I've been engaged with UAMI. We've been working on legacy parts, the NSNs. And so my question is, with the digital mapping, is that something that can be utilized for some of these complicated NSNs where there may not be engineered parts that we can use to recreate them?
I think you're talking, when I was talking about A10, is that the part mapping you're talking about?
Yes,
So that is actually tying information to an existing part. So in terms of maintenance records, I'm not sure they go beyond that, but I don't think it's the solution to the question that you're asking.
Okay. Well, maybe I could have a conversation with you offline about it. I'm very interested to see if there's a way to apply that.
Okay, I'm happy to that. And I'll share it with the community. My email is very simple. It's angela.timoficic@us.af.mil. Just got to know how to spell my last name. And I'm open to any follow-on questions you might have. And you can email me directly.
That's very generous of you, Angie. And again, thank you for taking the time. I know you're about to board a flight, and it ended up working that you're able to dial in and be part of this live conversation. Anyone have any final questions for Angie?
Hey, ma'am, this is Tim Bunning. Hey, Angie, how are you?
Hi, I missed the name.
This is Tim Bunning.
Oh, hi, Tim. I punted to you.
Yeah, that's okay. I'm used to it. Hey, it was a great talk. And I guess I'm looking for your opinion on, I mean, you talked a lot about existing high-end systems we have in the fleet today and the sustainment that we're going to need. But as you well know, your former boss and the department is trying to shift into, maybe a platform it's a little more attritable, a lot cheaper, may not need the extensive sustainment down the road. And to me, that's going to put a lot of stressors on our acquisition system that currently aren't there right now. It's somewhere between a weapon where we use once and something between a B-52, which we use for 70 years. And so I'm just wondering at your level, how are the I don't know, the requirements, how's the thinking gonna develop to try to enable such a system to become part of the force? Over.
Part of the enterprise. So these discussions are actually currently ongoing. Our current chief of staff is very interested in, and what you're talking about is E-Series. So they're very strong proponents of NGAD and the E-Series concept, Digital Century Series. You'll also hear that term. And it takes the entire enterprise to come together from R&D through depot and field maintenance to align to that concept. So I can't go into a lot of the details in terms of the strategies, but it is going to reinvigorate the industrial base as well as realign some of the activities that we do internally. And it's going to require an investment. So to think about, you talked about more attritable. I'm not sure. So there is that piece going on too. But if we think in terms of NGAD and the E-Series programs, that the concept is that we actually divest at the end of a certain time. So you're going to do that modular nose cone, that clip that I showed, in terms of upgrading capability rapidly, but you are, no kidding, going to divest at a certain time. So those go away, new ones come on. So it is a whole different mindset in terms of how we approach acquisition, how we rapidly field capability, and how we maintain that. I hope that kind of scratched the itch.
Yep, it does. I mean, just checking what your feelings were. I concur 100%. Over.
Just a little over. Well, thank you again for everyone for participating and asking your questions. And thank you, Angie, once more for being so supportive of all of us here in Utah and for serving our country in the capacity you're in right now. It's very valuable for our nation to have you at the helm of this effort. Thank you. And unfortunately,
thank you to Linda and Brent for the invite.
Thank you. Very good. So we will move on to our next speaker. Here we go. And we are going to talk about the subject area that Angie was just talking about with the Agility Prime and AFWERK. Unfortunately, we literally had a last minute within the last few hours that Colonel Diller was not able to join us today, but he was able to get his very able, very capable deputy of Major Tickle to join us and to present this concept and all of the new ideas and innovation that is coming out of Agility Prime and the AFWERK program. So I'm going to stop sharing so we can bring Major Tickle on. I see that he is part of, and we just need to unmute him.
Hi, good afternoon, everyone. Can you hear me?
Yes, we can. Again, thank you. Talk about a last minute step in. I really appreciate your being able to join us today and talk about the really exciting work that Agility Prime is doing with AFWERK.
Yeah, absolutely. And I didn't see which slides you were pushing. If you don't mind, I'd like to push maybe a different set and speak to those.
Diller didn't provide any slides. So if you have slides, I've stopped sharing. You should be able to share your screen.
Great. Okay, you see them up?
Yes, they're up. Thank you.
And then I got some notes to keep me on track here. How about that? So yeah, thanks for the introduction. Really glad to be here with this symposium today and have this opportunity to talk to everyone about AFWERX and then dive into the details of the Agility Prime program. For context, I'm going to go through and give an overview of AFWERX first. It sounded like there were some questions about maybe some potential Air Force programs. Maybe I can dive a little bit into those. Those aren't necessarily the focus of the division and the prime area that I'm going to focus on, but AFVentures and Spark may be some solutions to some smaller companies out there. So as of June 2020, AFWERX has really matured from a startup organization running with some phenomenal ideas with a small team and a small budget. Now the Air Force senior acquisition executive and other Air Force leaderships decided it was time to scale up the organization. So with that, AFWERX moved from headquarters Air Force staff, so you see it says transition A8 to AFMC, so that Air Force level staff to the research laboratory under Air Force Materiel Command, AFMC. And the Agility Prime program and Prime concepts was added to the traditional Spark and Ventures concepts, and then we end up with the AFWERX of today. So our mission and vision statements really combine the three main AFWERX divisions, and I'll run through Spark and AFVentures as an overview, and then we can focus on the Prime division and Agility Prime specifically. So in this slide, we see some clip art, right? That shows the Air Force has outstanding talent base. And the industry has the majority of the technology base. And for that matter, industry has the R&D funding base as well, with over 80% of the U.S. research and development. So, but we, the Air Force, also has a system that traditionally does not absorb or utilize this huge commercial investment in R&D. In fact, we have a place for a lot of this technology to go and die, and that's what we refer to as the Valley of Death in DoD acquisitions. So that, yeah, just where the great ideas and technology never really transfer to capability for the warfighter. So AFWERX intends to address this problem. You can start to get a picture of the synergy of the AFWERX divisions with these overlays. If we overlay the Spark program to engage the workforce, the Air Force Ventures program to collaborate with industry, and then the Prime program to focus on specific lines of effort for technology transfer, we end up getting more capability to the warfighter. So we've also added some locations as part of that scale-up effort to include our new sister service down in LA and the Space Force, a focus area for digital engineering in Dayton, Ohio, and to better and more closely coordinate with the Defense Innovation Unit, DIU, up in Silicon Valley. And we'll start off with a quick overview of AFVentures. For those of you who are unaware of the AFVentures programs, they run the Open Topic Small Business Innovation and Research Program, SIBR. So I'm realizing now that the slides are getting clipped in presentation view. Apologize for that. But the Open Topic SIBR program is really where a door for many small companies to come in with their technology and go through a technical evaluation and a business evaluation, and so that the Air Force can kind of determine the feasibility of working with those small companies. And then the F Venture is also running the supplemental funding pilot program, and also handle strategic investment. So a good amount of funds there. The concept behind F Ventures is, again, to create a lot of small bets for the Air Force to determine the feasibility, like I was talking about with SBIRS and SITRS. That's the Small Business Technology Transition program as well. So there's this SBIR and STTR. Then to make some medium bets with larger fund limits for prototyping, and then scaling products that work with the Air Force customer with Phase 3 SBIR awards. And then this next slide.
Major, your slides are running off. Can you adjust to a different Zoom level so we can see the whole slide?
I can try. That was just the presentation mode.
Oh,
it looks like every time I hit present, I think it's the aspect ratio of the slides is probably not the.
Okay, you had it just a second ago. Try whatever you did. Yeah, maybe. Yeah.
I mean, I can do this.
Maybe we just run it in this. Yeah, you can't see the words so well, but.
Yeah, it's just. It's not cooperating with this aspect ratio of the slides. I apologize for that.
Okay.
I don't think if there is anything important clipped off, I'll have to just brief to it. So here we just show some of the wins from 2020 and some of the goals for 2021. And then what is kind of clipped off there is one of the goals, to have a 5-to-1 return on investment. So for every dollar we're spending on R&D, industry, and commercial investors are spending $5 on that same technology. So the Air Force is greatly leveraging that investment by the commercial side. And then you can see some of the growth in the program here in the slide. For Spark, it's looking to expand and empower our existing talent and cultivate innovation. So you see 7 focus areas here where Spark is using local Spark cells mostly at different Air Force bases, but it's outreach to solicit lots of ideas from lots of people. Spark is investing in our people similar to the way F Ventures is investing in industry. So you can see the small, medium, and the last thing is big bets at the bottom there, where we're focusing on tens of thousands of people's and ideas in the Spark cells, offering part-time fellowships for a lot less people as a medium bet, and then big bets, creating an entrepreneur capability to bring people in and run a really big, like a moonshot type project. Large scale programs. Here you can see that Spark reaches all corners of the globe, being on those different bases. So really able to get a lot of outreach and touch a lot of different mission sets. similar to Ventures, some 2020 metrics and 2021 goals. Really, it's growth. So growing the number of Spark cells so that we reach more people, more ideas. Growing the number of challenges. And being able to handle the larger submission sets from within the Air Force. And so lastly, I've got the prime division here, and we'll focus on this. What's cut off there, it's emerging dual use markets, and that's a primary focus for the prime division, that it's dual military and commercial use cases for the technology we're going after. And that's how we get, that's part of our strategy to achieve a 20-to-1 return on investment in the prime division, leveraging a significant amount of commercial investment from the auto industry mostly, but lots of other venture capital out there putting lots of money into the eVTOL technology in Agility Prime. So we've got a lot of partnerships. We're coordinating with a lot of folks in industry, the investors, other agencies, the labs, the acquisition community, and also the last but not least the warfighter themselves, bringing them in early and giving them an early look at the technology. So what is Agility Prime? Really, it's being talked about as a third revolution in aerospace, where we see a coalescence of advancements in electric technology, autonomy, and manufacturing technologies. So for electric systems, we went from piston propulsion to jet engine propulsion to now we're looking at the battery technologies, where we can look at all electric propulsion technology. For autonomy, we've gone from stick and rudder, push and pull, to fly-by-wire, and now we're looking at AI and simplified vehicle operations in these aircraft. For manufacturing, which is what most of you are interested in here today, we've gone from sticks and paper in the Wright Brother plane to really the metal age with aluminum and titanium, mostly parts. And now we're looking at a lot of these companies have a significant amount of additive manufacturing in safety critical areas of their platforms. So additive manufacturing becoming a very critical piece to enable the eVTOL world. And if you're looking at the upper right picture, that's a picture of one of our one-seater aircraft called the Hexa, produced by a company called Lyft in Austin, Texas. There are some other more like 4 to 5 passenger or cargo type aircraft. You saw one on the previous slide. You see one in the bottom left there is in the same category. The bottom left is the Alia 250, produced by Beta Technologies in Vermont, and the previous one was the S4, produced by Joby out in California. And the Joby aircraft all of these are really far into flight test right now. These aren't concepts on paper. These aren't. These are real aircraft in real flight test programs and moving very quickly. And it's really not the right term, but because none of these aircraft are meant to be on the road, but these are flying cars. This is the flying car concept. So that's what Agility Prime really is. Why are we doing it? We have an opportunity to, we the military, the Air Force, have an opportunity to accelerate this industry by helping build the domestic industrial base, because this is supposed to be, Morgan Stanley predicted a $1.5 trillion market. I think it was by 2040. So we want to build a domestic industrial base so we don't repeat the mistakes that we made in the small drone industry, where we're now trying to catch up to companies like DJI and China who dominate the market. The process, so we have an opportunity with Agility Prime to change contracting processes, to change certification processes, to handle budgets a little bit differently. So it's an opportunity to improve acquisitions for the Air Force. And then the product, we can field a new air mobility system by 2023, looking at over 20 use cases that we can use these as is commercial vehicles for military operations. And we're developing those in detail. So how do we do those things? Risk reduction. So we're doing technical risk reduction by providing government resources to test and evaluation ranges, to providing test and evaluation equipment and SMEs, subject matter experts, trying to reduce the regulatory risk by introducing the military airworthiness process, which is a risk-based review of these platforms, giving them a lot more than an FAA experimental certification to see where the companies can mature and do more tests and gather more information to reduce the risk towards certification, type certification with the FAA. And one of those risks is additive manufacturing. Well, there's not a whole lot of confidence from the airworthiness teams in additive manufacturing, especially in those safety critical areas that I was mentioning before. What else are we doing? Financial risk. We're investing in these companies. It may be a lot smaller than what commercial investments are doing, but we're providing confidence to the investment core within the U.S. By being able to look at all these companies doing these airworthiness evaluations and providing levels of funding, leveraging the AF Ventures program. In just over a year since we've launched the program, we've set up and had 27 companies come through our air race to certification. 3 companies have actually it's 2 companies have completed the airworthiness process and flown for the Air Force, and then there are I believe 4 more in the queue. So of the 27 companies making it through, only a couple making it to the airworthiness process, but now flying on Air Force contracts. We've been able to award over $100 million in contracts, leveraging SBIR money, phase 2 awards, and then we had the open topic STTR that ended up with 254 STTR contracts. So that's the small businesses looking for a front door to the Air Force applying to these STTRs, going through an evaluation, and us saying, yes, we're interested in your technology. We're interested in your technology for Agility Prime, and let's give you an opportunity to walk through your capability with a phase 1, try to match you with a company or a partner through collider events, through trade shows, through just open communications, so we can partner you with these other startups and have the opportunities to work with the Air Force. There's been co-investment over $1 billion in commercial investment in several of these companies. They've also some of them have gone public, receiving valuations in order of magnitude of $6 billion. We partnered with Air Education Training Command to develop training for operators of these vehicles, to develop training for the maintainers of these vehicles. And then we've actually had hardware delivered. So there's multiple lift hexes. There's a charging station. There's simulators that have been delivered to Springfield, Ohio, and are in the works of delivering more aircraft. Let me go back and just talk to the potential missions real quick. So a lot of interest in search and rescue. That's the CSAR acronym there, is combat search and rescue. And then we have distributed logistics, emergency response, and even firefighting. So a lot of interest out of California in using these to help get people and equipment to help fight fires. And then what do we want to do with other prime programs? So we have Agility Prime. What does the next prime look like? And these were the 6 other opportunities. And I'll just read what's cut off there. For Energy Prime, looking for novel energy generation, advanced storage, and alternative transport. For Vector Prime, that's supersonic transport with hybrid propulsion and quiet supersonic designs. Then there's the microelectronics prime potential, improved performance, secure technology, and anti-tamper. Then the other ones are there available for you to read. But the idea is that there has to be commercial dual use case and strong commercial investment in these areas for them to proceed as a prime. So these are all concepts as of right now. I think Space Prime has been chosen to move on as to be the next prime, and the others are still undergoing a series of more we're looking at them more closely, more study. That's really where I was going to end and go to questions, if there are any questions.
Thank you. What a great presentation and what an amazing program. I have a quick question. Okay, so we have Angie who spoke, and I guess she's at the Pentagon and headquarters. And then we have AFRL, Air Force Research Lab, which we're going to hear Tim next talk about. So how does AFWork fit in to the puzzle?
So AFWorks is now a directorate within AFRL. However, it is also, the director is a direct report to the senior executive of the acquisition senior executive. So it was Dr. Roper. Now we have an interim at FAQ 18L. So Mr. Bunning is on and said he'd like to answer that. Actually, go for it.
Oh, okay.
Yeah, well, I was just going to add to it. I mean, so in the Air Force, there's a term called operational control and administration control. We call those two OPCON and ADCON. So right now, AFWERX, as the major stated, fits in AFRL. They're part of AFRL. They're a functional directorate. They get their ADCON, organize, train, and equip, from General Pringle and the group that I'll discuss here in a little bit. Their OPCON, where they get their strategic guidance and go-dos, has historically been the SAE, the Senior Acquisition Executive, who is Angie's boss. With the administration change, we'll see how all of this plays out. But that's the current model right now. Over.
Oh, thank you. That has been confusing to me. Now I understand why. Thank you so much, Tim. I appreciate it. Other questions for AFWERX and Agility Prime and Space Prime that you just threw out there? Just unmute yourself if you have a question and you're on WebEx. Or Kathy, do we have any questions coming in from the YouTube feed?
So far, just one question. Will the slides be available to the participants?
Yes, they will be.
Thank you.
Anyone out there want to ask a question?
Yes, this is Marshall Wright. He alluded to the fact that they were working with the FAA such that they would not repeat the faults that ended up with small UAS. How is that going?
So I think I was specifically referencing the Chinese company DJI's capture of the market overseas, and the Air Force then had to develop and develop a domestic capability for military use and operations. And we were way behind the power curve, and still are in the market compared to DJI and their capabilities. And we didn't want that to happen in this new emerging field of eVTOL, and then have to catch up again. So we are currently the leaders, and have U.S. companies are definitely leading these efforts. There are several international companies that are doing pretty well. They have their own companies. The Chinese EHang, the Germans have two companies. I think they have Volocopter and Lilium. But there's lots of international competition as well. But I think the American companies are definitely the leaders in this case. As far as interacting with the FAA, absolutely. So that's part of our interagency coordination, coordinating with NASA, coordinating with the FAA on issues like airspace management, on issues like public acceptance, on certification. The FAA is definitely being very responsive, and I think they've learned and are starting to adapt to the needs of a rapid changing and a third revolution in aviation, like I was talking about. So we're in close coordination with them. For example, we have these simulators that are being set up, and the FAA is going to come to these simulators to fly the aircraft to better understand their handling qualities, their safety features, their just how they fly in general, because there's a lot of different concepts out there, but you can go fly the individual sims and get a bigger picture of what's going on. Thanks for the question. Yeah, that's a great question.
Well, very good. Chanel Flores, who is Deputy Director of UAMI now, would you ask our question that we've been wrestling with about getting composites certified?
Yeah, so one of the questions we have is around the certification process of new materials. It's oftentimes an expensive process for, a smaller company to be able to look at certifying new materials. And so we were just wondering, what is being done around, you talked about certification of airworthiness, but what is being done around certification of new materials? And do those new materials, are you guys looking to require the digital thread behind them?
So I think our support of the STTR process and our investments in research of any companies looking to do the certification processes is the level of depth that the Agility Prime program is participating in that specifically. So if a company is struggling with that, what they would do is propose to the Air Force the steps they need, and we would help fund that effort through an STTR or through an SBIR. And that's really looking to for the commercial and industry to engage the Air Force on the topic versus the other way around.
Thank you. Well, thank you, Major Tickle. First of all, for stepping in so aptly at the last minute. Really appreciate it. And I look forward to hearing more about AFWERK and Agility Prime and all of the great work that you're doing. We're going to have to move on to Mr. Bunning's presentation on AFRL. But again, I thank you and thank everyone for your questions.
Yep, thank you. Bye.
So as I said, our next speaker is now somebody well familiar to us, Tim Bunning. He's been our #1 question asker in our presentation so far, and we really appreciate your adding some clarity and some perspective. So we're really pleased to have him today because he's a member of the scientific and professional cadre of the senior executives, and he is Chief Technology Officer for the Air Force Research Lab, which is, as we were just discussing, at one of the epicenters for being able to conduct this research that we've been talking about. So without further ado, his full bio is part of the agenda that, again, you can find on the website. I'll be running his slides for him. So Tim Bunning, you want to take it over?
Sure. Can everyone hear me?
Yeah, we can.
Can you see me as well?
And we can see you.
Okay, great. So it's certainly a pleasure to be here. Topic from my own heart. I spent 5 years as the chief scientist of the Materials and Manufacturing Directorate within AFRL. And then I grew up in that directorate as part of my career. And so coming back to materials, coming back to manufacturing is getting to my roots. I wish this meeting was in person. If it was, I probably would have spent last night with my good friend, Mr. Lockhart. We probably would have had a few beers. We probably would have solved a whole bunch of problems that neither of us would have remembered this morning. But I miss the ability to get out and interact and interface, and look forward to the times when they change and allow us to, and I'd love to come out there. So next slide, please. I was asked to sort of give what I consider to be a list of the key research areas for AFRL. And I'm not going to do that, and I'll sort of give you a why in a moment. But I will give you a sense of what we're sort of pivoting to. There are many lists out there, and I will share some of them with you, depending on who you are, where you sit in the ecosystem, whether you have a near-term view, a mid-term view, a far-term view, whether you have a structural materials bent or a functional materials bent. You bin yourselves against one of these lists. There are lots of crystal balls out there, as people know. If you would have asked us 5 years ago, would we be in the pivot that we are in right now, per the National Defense Strategy, which was just published a couple of years ago? We would not. And so people build these lists and they put a vector out there and they assume they know what that future is going to be. And I always say that the crystal balls are very, very fuzzy. And then obviously there's rapid geopolitical changes going on. We are in a war with some near peer competitors that we were not in a few years ago. That war is geopolitical and technological right now. We are losing that war in terms of all measures that we use to look at these things. Percentage of GDP going into next generation capability, scale up of the military, number of STEM graduates, number of patents, and my roots, which is a little more academic, just look at the burgeoning quality of high-notch technical papers coming out into the literature. And so those three things, are paint a picture where AFRL is undergoing a massive adjust, I would say. And so I think the better description of what I'm going to talk to you about today is what are those macro changes ongoing in AFRL. I'll first give you a sense, make sure everyone's on the same page of what AFRL is from where I sit. And then I will give you a sense of what those macro shifts are, and then be happy to take questions. So for those of you who don't know us, and I apologize for those who do, I mean, AFRL is a pretty big place. It's executes on the order of about $2.5 billion in core funding, and I'll touch on the flavors of that here in a little bit. We execute another $2.5 billion of other people's money. We believe that's a sign of strength. That means people are coming to us because of our technical prowess, because of our technical capabilities in testing, that they entrust us to shepherd and execute those dollars. About 11,000 employees, about 1,000 of those are military, about 5,000 of those are government. Of those 5,000, probably 3,500 are what I would call S&Es, scientists and engineers, and over 60% of those have at least a master's degree. So fairly highly educated workforce. And then we also have quite a strong, what I would call on-site staff position that's used to supplement our workforce to provide continuity in some of the testing, and quite honestly, to provide some agility that the government workforce doesn't provide. We are all over the map. I'll show you here in a little bit, but generically, we stood up about 25 years ago through the consolidation of 4 former Air Force laboratories in our basic science branch, AFOSR. So next slide, please. So I can't give a brief without the proverbial org chart. This will help a little bit with the answer to where does AFWorks sit, who's who in the zoo, as they say. So AFRL is a big place. We're led by, it's now Major General Select Pringle, my boss. that sits at the head shed. You know, a lot of you probably know Jack Blackhurst, has been around for a while. I'm what's called the Chief Technology Officer, really the senior science and technology advisor to AFRL, to the general, and everyone, anyone who will listen, as they say. The dark blue boxes are what we would have maybe 7, 8 years ago called our core AFRL. The blue boxes are called technical directorates. They are organized around technical disciplines, things like materials and manufacturing, things like directed energy, things like space vehicles. Off to the left, we took on part of the medical mission a number of years ago, and so that's colored a different color. They have a dual reporting chain up through the acquisition side that we just talked about in the classic AFRL reporting chain, but they also report up through the Surgeon General office, and they do a lot of training for medics, doctors, nurses, etc. All of the Air Force medical staff come through that part of AFRL through what's called the schoolhouse, and it's where we educate our personnel on the medical side. Off to the right, we mentioned AFWorks, relatively new, colored in orange because, again, different OpCon, AdCon. Their AdCon comes from us. Their OpCon comes from the SAE, the Senior Acquisition Executive. The two at the top, SDPE and the Transformational Capability Office, again, different color, different OpCon, AdCon. In this case, the Developmental Planning and Experimentation Shop, of which Mr. Lockhart was part of building and getting to full operating capability. We get OpCon from the chiefs, I would say, and then again, AdCon through the AFRL side of the house. So my point in showing this slide is everyone assumes AFRL is a pretty homogeneous system. It is not. There's lots of different color threads. There's lots of different bosses. There's lots of different reporting chains. And it makes my boss's job, General Pringle, very, very difficult sometimes. Next slide. So geographically located, I won't spend a whole lot of time on this slide, just to show you the main locations. We do have an international presence through our basic science office. We have an office in London, an office in Tokyo, an office in Santiago. Soon to be added will be an office in Australia. So again, pretty extensive footprint across the country. Next slide. So I'll spend a little bit of time on this slide. Depending on who you are on this call, you know, one of these boxes means more to you. If you're from academia, you're primarily interested in the left-hand box, basic research. That's work that's primarily funded out of our Air Force Office of Scientific Research. This is primarily grant money. This is money that is issued to academic professors, you know, through competitive proposal writing. Roughly 70% of their money goes to academia on the outside. Roughly 30% goes to fund basic science work within the lab, and then to build that bridge between the two. The 6.2 box is what I would call tech push. So that funds a lot of the government salary, a lot of the on-site technical capabilities that we have as a lab. It does some external work, a little bit of external work with academia, and some external work with industry, but more from an early TRL level, more tech push concept exploration. The 6.3 side is where we typically do our larger demos. This is done primarily with industry, primarily not exclusively, but you know, this is where the big boys come in, the OEMs, the Raytheons, the Boeings, the Lockheeds, etc. And you know, typically these are contracts where we do risk reduction in industry. on a capability, a technology, something that we are pushing forward. I like to use this comment because I think it's sometimes lost on people, but that the Air Force, the big Air Force, the operational Air Force, does not buy capability from AFRL. Our job is not to provide capability directly to the operational Air Force. The operational Air Force buys capability through industry. They buy capability through industry. Our job is to work with industry to reduce risk on concepts and topics that near, mid, and far term Big Blue might want. The SDPE 6.4 money been a strong push in this area over the last few years, trying to do more what I would call experimentation out in the field with real working prototypes, typically expensive, typically have the test ranges involved, test review board, safety review board, things that you're not going to do, in a more laboratory environment. And so that's been a growing pot of work going on. And then, as I said, we leverage quite a bit of other money. The AFWERX money that we just heard about would fall under this bucket of money. It's a different color money, again, executed for Air Force missions. With all that said and done, roughly 50% of the pot goes into salary and infrastructure. And so there are some that say, well, you have $2.5 billion. Why can't you go do whatever you want? Well, I mean, there's a lot of sunk costs, in that $2.5 billion. As I mentioned, and as this slide describes, it's not a single pot of money. There are a lot of multiple colors, and there's a lot of owners and a lot of customers out there, all of whom would argue that they're not getting their fair share of AFRL resources. And then, we tend to have these cycles of what's in vogue, what isn't in vogue, near, mid, far, what's the role of the lab. I would say there's a panic going on in the Pentagon right now. The fight has changed. Everyone doesn't know how we're going to win in a fight with a different competitor if we had to go to war, 5 years from now using the equipment we have today. So that's driven a hyper focus on maybe trying to up our game in the near term to alleviate that fight. And so that's a stressor that's going on right now within the community. Next slide. So some key lists, lots of them out there. National Defense Strategy said here are the most important things we need to go work on. On the right, OSD, Office of Secretary of Defense, they have their what are called top 11 modernization priorities. They come down to the labs and say, these are the 11 most things you need to be working on. Air Force Futures, which is a group that stood up to look at an alternative fight to help big Air Force figure out how it's going to win in a different world with a merger of new technology coupled to the existing platforms we have. So they come up with their list. These are the areas that we really need to get after to deal with a peer fight in a contested environment. Next slide. And so, my point here is to say we can align ourselves with any of those lists, and we do, depending on who asks the question. From an internal perspective, an inside baseball perspective, we see ourselves as core technical competencies. We have a vibrant, constantly changing set of core technical competencies and the work that's going on underneath them. Right now, there's roughly 30 of them spread across the technical directorates. We shift based on the demand signals, and I'll give you a sense of what some of those demand signals are here in a moment, which will give you a sense of where we are macroscopically changing our research areas. But as part of this bookkeeping, if you will, we routinely capture areas of increased emphasis. So these are areas where individual organizations have said we're going to put more money in this versus that. And areas of decreased emphasis, and so we like to have this out front. Sometimes the knock on the lab is you guys keep working the same old things, and I would argue that's just not true. We're constantly trying to adapt to what the demand signals are. Next slide. So we are pivoting. Just to give you a sense, we had pivoted in the past, so this gives you a sense of some of the macro changes. There are four. I would argue that we are pivoting right now at a scale and at a magnitude that we've never had to pivot before in this certain time frame. And it's driven by four concurrent activities that have happened. And if you hit the next slide, on the bottom left, the publishing of the National Defense Strategy. You should Google it if you haven't read it. This is about, the fight in the desert is no longer the fight that we need to be prepared for in the future. And it gives you a sense of what we need to do differently. The research lab, in part due to that, took a step back and said, what do we need to be successful in the future if what we have today is not going to work? And so we generated and published what's called a Air Force Science and Technology Strategy. It's called the 2030 Strategy, looking at how we needed to change. And so there's an implementation plan for that. And so we're trying to drive lots of new activities to help us pivot based on the tenets that are in that document. The upper right, about 14 months ago, December 19th, 2020, no, December 20th, 2019, I always get them confused. We stood up a separate service, United States Space Force. And instead of standing up a separate research lab like Army has ARL and Navy has NRL, the Air Force Research Lab was anointed the one lab for two services. And there's lots of reasons why. I think it's a smart move to do that. But as the Space Force has matured and developed, and their priorities getting more and more high-level visibility, it has forced a pivot in terms of where the Air Force needs, where the AFRL needs to pivot its resources. And then the fourth macro change, which we just heard a tidbit about, is the incorporation of AFWERX into our ecosystem. Absolutely critical. I don't know what happened. I lost the slide. Anyone else see the slides?
I'm sorry, it must be me. Just give me a second. I don't know what happened. Somehow I lost it too. There we go. I think we're back.
Okay, great. So AFWERX coming into our ecosystem is timely and it's needed. And the ownership of R&D by the military, where it used to be 80-20 military, 20 commercial, it's flipped. And so the entire ecosystem needs to do a better job of coupling with commercial. And as the Agility Prime discussion showed, tapping into commercial and venture investments in areas that maybe we never really thought about using for an Air Force mission, but can we leverage that to think about how we might incorporate that so that, again, it's all about the fight with a different near peer so that we don't lose the market like we've lost the market on so many critical technologies to overseas. And so having AFWERX come in, as powerful as it is putting stressors on an ecosystem that is just not used to dealing with that. So that's led to four what I call macro shifts in the portfolio. And then I'll get off the stage here. Technologies for the future fight. Like I said, the future fight's going to be different. We're not going to be able to fly our F-16s and F-22s in there and have tankers out there that can fuel them whenever they want and get in there whenever they want. It's a contested environment. It needs a different set of warfighting capability. And that's driving a whole discussion of what are the other things we need to do to make sure that we can survive and thrive in a contested environment. And so AFWERX futures priority list is shown there. I'm not going to go into detail. To me, there are 5 major drivers. One is we really need a connected sensing grid, something that's joint. We have 3 airplanes right now that are all manufactured by the same company who can't talk to each other. That's just not going to fly in the future. So we really need to build a kill web, if you want, a mesh web, a connected sensing grid that not only connects the Air Force activities, but Space Force, Army, and the Navy. And that's putting a lot of emphasis in the IT side, and things like ABMS and JADC2, which have been in the press a lot, are really the impetus for that. Really need to affect target to include left of launch. You know, it's about deterrence, you know, and if they know you can do things left of launch, they know that that we can see, etc. So things like cyber, things like space, SSA, etc. In a fight over there, the tyranny in distance and time, you know, if you look at a map, you look at the Pacific, you know, it's not easy to get over there. It's not easy to bring effect on a time scale that's relevant. And so how do we do things differently? Acknowledging that it'll be contested. We probably won't have runways. We probably won't have GPS. You know, what are the things that we need to be doing as a service down the road to build those capabilities? And then, as I asked Angie earlier, you know, as part of that, you know, there's a sense that we're going to try to shower them with mass, low cost, lots of vehicles, you know, to make their world a lot easier. We're just not going to be able to afford to send in lots of high-end platforms and lose them. And so, you know, there's a big push right now to do attritable low-cost vehicles and all of the technologies that go on to it. Angie talked about E-Series. I would say there's a series even below that too, somewhere above a munition, but things that you've heard in the press, or may have heard in the press, things like Skyboard and Golden Horde of, you know, things that are coupled together, but that we are not too worried if we lose them. Next slide. Space priorities. Again, lots of technology pushes here, and I'll just say it's a stressor. It's a good stressor, I think, for AFRL, who has primarily probably unconscious bias towards the air domain. Space world is completely different now, completely opened up, and you know, it's a warfighting domain now. And we used to not say that in public, but that's being said in public right now. And if you look at the explosion of people up there, if you look at the explosion of things that are up there, and you look at the explosion of what, you know, our near peer competitors are doing, it's mind-boggling. China just landed a rover on the backside of the moon. You know, so it's something we need to be worried about. And that couples into this discussion we were just having about AFWERX, and that is, and I think space is a great example, you know, that there is a push to partner with non-traditional, and instead of the lab having an invented here syndrome of we're gonna, you know, me and my sandbox is gonna push the thing that I invented. We really need to look to commercial, rapidly adapt commercial, be able to partner with our partners, particularly international partners, at a scale that we haven't been able to do before. Next slide. And then this is really more of an internal look. So macro shifts in the portfolio as it relates to AFRL, you know, more from an ops perspective. Angie talked about the digital trinity. Those are the three things there. You know, AFRL is also trying to pivot, you know, digital engineering, agile software, open systems, all of the things that we're trying to push into industry. How do we have a workforce that's more digitally literate? How do we enable our business systems to be more digital so that we can function quicker? You know, everything that we need to do within the family, as they say, to go digital is a big push right now. Trying to do transformational capability development on a time scale differently than we've done in the past to get after this valley of death discussion that we were talking about before. And then again, I would argue, you know, AFRL has phenomenal people. They do phenomenal things. They're providing product every day. But the one knock from my perspective is we work in what I would call cylinders of excellence. Each of the TDs, you know, is their own little ecosystem. And I really think for the fight that we're going to be in, we're going to have to be working multidisciplinary solutions and teams. And so there's a real push internally to try to get some better coupling across the AFRL cylinders. Next slide. So going back to Mantech, manufacturing, my roots. So as you know, the Materials Manufacturing Directorate within AFRL is the executive agent for the Air Force Mantech program, the DPA, Defense Production Act work, all of that sort of stuff came out of, it sits in that directorate. They have a strategic vision on the upper left, lots of great historical impacts that they've made over the years, which JR will be on later, I'm sure he can talk to. But just to give you a sense, they are also trying to shift and some current foci, again, coalescence of digital design with digital manufacturing to maybe not get after to the question earlier of how do I remake something, but how do I make those things that I can't make now any other way? What design space does that open up to allow me to do something differently? Lots of discussion on AI and robotics and automation from a manufacturing perspective. Lots of concern about industrial base health. I mean, as COVID thing has seen, the DPA, Defense Production Act, has really ramped up, and Chuck Ward, who I know some of you know, has done a great job scaling it up. There's also a lot of concern with the supply chains right now. So there's lots of small companies out there that if you do some deep analysis, you maybe don't want to be interacting with because of who they have ties with, who their investors are, and I think there's going to be a more, I don't want to say scrutiny, but there's going to be more awareness that we need to understand who we're working with. Trying to go to open systems and open up the tech data packages to again get after the digital trinity, and then emergence of non-traditional manufacturing techniques. The bio ecosystem is a big ecosystem. There's lots of Air Force needs there. But when we typically think of manufacturing, we think of casting and, composites and, the more classic structural materials, but there's lots of manufacturing needs on the more functional material side of the house. Next slide. So how do you work with us? I would say there's three major ways. I would say a lot of people look at us as a funding source, which I don't really like. I think our job is really to work collaboratively with university and industry. We understand the state of the art as well as you do in your local domain. And when you add those two things with our understanding of the warfighter needs, we can get after some things to really do a better job of connecting and developing and exploiting the S&T that we need to go. Direct funding, we put, probably half of our money out on the street in one way, shape, or form, again, to reduce risk in industry via the TDs, via the Mantech program. With academia, we do it primarily through OSR. You just heard about the AFWorks ecosystem, trying to get after, a different set of practitioners, if you will, than the normal ones. We do a lot of partnerships, including the Mantech Institutes that Angie referenced earlier. They are executed out of our AFRL Materials Manufacturing Directorate. And then, again, pre-COVID, through lots of information exchanges, and look forward to helping connect the dots on any and all of these as the case may be, given the perch that I sit in. Next slide. I think that's my last slide. Yeah, so again, here, a couple of websites. My email is here. I'd be happy to take any questions with the group. Happy to answer any questions one-on-one via email. And, don't be shy. We're all part of the same community. Over.
What a fantastic presentation. Thank you so much. We really laid it all out, understanding the structure and pivoting. And I'll tell you, as a U.S. citizen, I definitely am finding comfort in knowing that we are really looking at this new warfare that we're getting involved with as being so different than traditional. Other questions? Do we have some questions out here? Kathy, do we have any questions from our folks on the YouTube?
I got a question.
Yes. Identify yourself.
This is George.
Oh, hi, George.
How are you?
Always count on you for a question.
Sometimes difficult. Dr. Bunning, that was a very good presentation and pretty comprehensive. In 2012, Secretary Gates put out a letter in which he said that electromagnetic effects and warfare and measures and countermeasures were in his top 5 priorities. And I don't even see the word anywhere in the presentation now. So it gets to be, where does it fit in? Because if we don't pay attention to it, we're going to wake up one day and our computers aren't going to work and our data is going to be gone and people are going to be getting sick and nobody's going to know why.
Yeah, so I'll just answer it this way. The reason you don't see it is because it goes behind closed doors very, very quickly. And we, you know, in a setting like this, we don't put it on charts. We don't talk about it. Over.
My apologies.
Good question, but it can't be answered. Are there other questions? Kathy, are there any questions from YouTube?
We just have one question. Who should we contact to present a company to AFWERX or Agility Prime?
So I didn't quite hear all of it. Something about a company, who they should contact with regard to Agility Prime? Is that the question?
Exactly. How does a company interact with Agility Prime? Boy, it's so easy to interact with them. Once you get hooked in, they become your best friend, right?
Yeah, I mean, what I would do is I would go to Nate, you know, or the major and say, you know, what's going on. I don't know where they are in terms of their solicitations and all of that, but there's definitely opportunity there. Over.
Well, I can answer that. You just go to their website, go to the AFWERX website, go to the Agility Prime section. That's where the STTRs are. That's where all of the videos from all of the working sessions that they've had are. And there are also links to directly engage. So it's very easy. And then once you sign up to be part of the ecosystem, as they say, you will be inundated with emails from AFWERX because they really keep in touch with the ecosystem as to what they're doing. They're very easy to interact with. Other questions? Well, you told us everything we need to know. Thank you so much. Really appreciate your participation.
Sure, take care.
Look forward to doing more things and working with you in the future. Thank you. So now we're moving on to our next presenter. Dr. Bunning talked, if you looked in one of his slides, he listed our national labs. And in today's symposium, we have 2 national labs that we're going to hear from. The first one is the Oak Ridge National Lab with Tom Kerfus. And we at UAMI, since Utah is so focused on composites and carbon fiber and advanced materials and new materials, have worked with Oak Ridge Labs in their composite program. So we do feel an alignment with the Oak Ridge Labs. So I'm pleased to bring on Dr. Kerfus, who is he's currently the Chief Manufacturing Officer at Oak Ridge National Labs, and he's going to share his own slides. Again, his bio is on the, let's stop sharing. His bio is on the website as part of the agenda. You can click on his bio and learn out more about him. And with that, I will turn it over to you, Dr. Kerfus.
Well, thank you very much. I appreciate the introduction. So again, I'm Tom Kerfus, Chief Manufacturing Officer here at Oak Ridge National Laboratory in Oak Ridge, Tennessee, just outside of Knoxville. And I'm going to be talking about the democratization of advanced manufacturing. And so the idea really is how do we get the latest technologies out there, and not just to the primes, but really to all of the suppliers, the tier 1, 2, 3, 4, 5 suppliers that are out there. Even the mom and pop shops that really make up the backbone of U.S. manufacturing. And so I'm going to do that, and I'm going to leverage some of our work that we're doing in the hybrid area, which is a combination of additive and subtractive. So first thing I want to do is thank a number of my colleagues, the good doctors Feldhausen, Salibi, and Paki. We have we have about 5,500 technical people here at Oak Ridge National Laboratory. It's a great place to be. Hopefully we see a light coming at the end of this tunnel. If there's an interest in particular in visiting the manufacturing demonstration facility, which is one of my facilities, you are more than welcome to come out and visit us. It's a very nice place to visit. And also thank you to Department of Energy for funding a good chunk of this work. As I said, I head up the manufacturing science division. Our unofficial mantra is innovating faster than the competition can copy. And really what that means is, look, let's take the latest technology and get it out there into production. And let's get the latest designs and start to produce them. And we'll use all sorts of different capabilities. We'll be talking about digital, but we have some of the large scale printers. You can go look up the 3D printed car. You'll see actually former President Obama and then Vice President Biden visiting us, taking a look at the car and so forth. But we do have things like metal powder bed. I'll be focusing on hybrid machining and even next generation production systems. This is Medusa. You'll see this in operation momentarily at the end of my talk. These are 3 robots that have big welders on them that are putting down metal onto this rotary table over here. So building large scale cylindrical type parts. Our vision is rapid innovation, ensuring U.S. dominance in advanced manufacturing. And really our mission is to identify and scale up as well as integrate critical technologies for new and emerging advanced manufacturing sectors. So there's an idea at a low TRL, let's say 1, 2, 3. We're here to help scale it up. And it's not just us on our own. We work with industry partners to scale that technology up, get it into production. I'm talking really more about the digital thread today. And so just to give you a feel for it, it's really about ubiquitous sensing, big data, and AI. If anybody has a kid in high school or even junior high, they're probably programming things like the Arduino over here. This is like $10, maybe $15, $30 for a Raspberry Pi. This system right over here has got way more computing power than what we used to put Neil Armstrong on the moon over 50 years ago. It's basically a Linux system. You program it in Python. And again, typical high school students are programming these. This is another one. This is the particle photon. If you see any of these little scooters that, I haven't been to a lot of cities recently, but if you see the scooters that are sitting around and so forth, typically driven by a particle photon. They're low cost, pretty much disposable. If you break it, you just go buy a new one, and typically that new one is going to be better than the old one, and in many instances cheaper than the old one, so rapidly upgradable. And then there are just a bunch of sensors out there that we can use. Sensors on the machine, sensors that we can add to the machine and so forth. And really what we look at is how we integrate these sensors together. So back in the old days, we might have a sensor or a machine, and then we'll get some information and we'll send it out to the network. Today, we really use a backbone, a communications backbone, and it might be something like a request and reply, like a REST, which uses hypertext HTTP. And so this is, we just say, hey, machine A, give us some information, and machine A gives us information. Or it might be publish and subscribe, something we might call like an MQTT. And these are just standard things that are out there. They're used everywhere. Amazon, standard type of usage, Google, et cetera, uses these types of things. And here we might say, hey, machine B, we're going to ask you, we're going to subscribe to your publication, and you're going to be sending information out. And again, that information comes out really in an XML type of file, or more recently JSON, which is just a little bit more of a compact version of XML, but very general purpose. And it really just allows either machine to machine or machine to cloud communication. No static IPs, which really do help you. I'm not going to get too much into the cybersecurity aspects of it, but that is a big one as you plug into these. But these really do help you in terms of cybersecurity. I will throw the cybersecurity issue up. About a third of all cyber attacks in the United States today are targeted on our industry sites. Frankly speaking, they're not really looking at damaging equipment or playing with the process, causing a turbine blade to be misprinted or mismachined. Mostly these attacks really are trying to get intellectual property. So right now, most of the attacks are against these manufacturing areas, trying to get information. We'll talk a little bit about that in a bit. But basically, once we have this going, you can send information up to the cloud. We also might think about the fog. So you've got edge, which is we're computing right here at the machine, right where the sensors are. We have got the cloud. I think people are familiar with that. And then we have fog where the cloud touches the edge or the ground. And that's kind of a hybrid, if you will, between the edge and cloud. So we would maybe do some processing here. If I need some more power, I can reach out into the cloud. Again, lots of interesting stuff going on there. But once you start to integrate these things, there's our friend. I won't say her name because many of your systems at home might light up. But basically, this allows us, these types of capabilities allow us to go right into it. You get to say, hey, my friend Amazon Echo, what is Machine C doing right now? Oh, it's building this part, and here's the runtime and the whole bit. So all of that is easily integrable given this type of architecture and structure. And certainly getting stuff out to a smartphone, again, these can be web-based or a tablet, is relatively easy. So it's very easy access, very low-cost computing, and very low-cost capability. To give you a little bit of a feel, these are just two different types of machines at some of our facilities. This is an Okuma, this is a Mazak. They're both running MT Connect, which is a standard protocol for communication. And in this particular case, we're just getting spindle speed directly off of the machine. And so now I can tell when my machine is running and when it's not. So we can take a look at machine utilization. In this particular case, the company we were doing some work with, they were making just one-off turbine blades, so just a replacement blade. They weren't making hundreds of the same type, and they were interested in how long does it take me to make a particular blade. Well, here's the time. I start my spindle here, and then it stops here. This is how long it takes me to take the blade. And so after about a year's worth of data taking, we could go back and run some statistic. They might have made 10 or 20 of these blades over that 1 year period. And now we can figure out, we can put together your standard control chart, X bar, S charts for this blade and maybe for this blade and so forth. And so relatively straightforward. This costs zero because the information is coming directly off of the machine. And the machine is capable of doing it. You have to connect the machine up to your network. Again, be very careful about connecting it up with cybersecurity issues. Lots of good opportunities to engage on cybersecurity as well. If the machine doesn't have a capability to be connected to the network, or if it doesn't have this the output capability, a very simple sensor like a vibration sensor. So just an accelerometer. Easiest one is probably a triax accelerometer. You can take an accelerometer, connect it to your Wi-Fi. So a Wi-Fi chip, actually accelerometer hooked into an Arduino. That whole package probably costs you $30 or $40. In fact, probably the most expensive part of a package like that would be the box that the electronics package goes into. So the processor, the sensor, the whole bit are cheaper than the box that it goes into to keep it protected in a shop environment. Machine is vibrating, I'm making the part. Machine is not vibrating, I'm done making the part. Now here's what's really interesting with this is once you have this information, one of the things I looked at is I said, oh, well, here we have the setup time. So this downtime is the setup time for this next blade. I already have all the data. Let's go compute the setup time. If I'm just making 1 or 2 blades at a time, it's going to be the setup time that dominates. So I took a look at it, and I said, wow, the standard deviation of the setup time for this blade is all over the place. It's super big. Why is it so big, for this, for any of the blades? It's really spread out all over the place. And what you learn, and again, it's not a big surprise, but unless you think about it and look at the numbers, you don't think about it. If this blade and this blade are very similar in nature and use a lot of the same tooling, setup time is going to be small. If these blades are very different in nature, I've got to do a lot of tooling changeover, setup is big. So one of the rules we gave back to this company is we said, look, to reduce your setup time, let's group, and this is something that you would normally do. Again, just didn't think about it. Let's group, we produce the first blade, and then let's pick a second blade so that it's very similar to the first blade. So you group them, group technology, group those blades together. we wound up with a 17% time savings or reduction in idle time on the machine tools. So it was just absolutely fantastic. And by the way, that's just looking at spindle spinning. One of my colleagues, he heads up our machine tool group over here, Scott Smith, he said, look, when he was a grad student 30, 35 years ago, we would spend weeks putting instruments on these machines, and then we would run experiments and analyze all of the data. Today, all of those instruments, all of those sensors are already on the machine. So every time we make a cut in production, we're running an experiment, and we can get information off of our machines. So these are the types of things that we actually look at, and basically the data are free. Now let's take a peek at some hybrid systems. So we're going to go a little bit more advanced. And hybrid is just a combination of additive and subtractive, which would be machining. So again, you're going to print some material out, and then you're going to machine it down to get the right shape. In this particular case, we are printing just this propeller over here. You can see that we've got all sorts of overhangs and so forth. But again, it's a 5-axis machine, so we're printing this while rotating. So in fact, we can, if you will, change the direction of gravity. So this allows us to print something like this propeller. And how we printed this propeller is we just started with a piece of bar stock and then printed the material on there and then machined it to a final shape, but printed without using the support structures. Typically, that's kind of good for these metal type of geometries, or when we're using metal, because again, it's not so easy to break away that support structure. So if we just take a look at hybrid, it's again a combination of CNC machining and additive manufacturing. On the machining side, it's repeatable, precise. We get good service finish, high productivity. But again, a lot of times you're machining away a lot of extra material. We can get rid of that when we're doing additive because we can just print what we would call, like a near net shape form. We call it a preform. We have a lot of geometric freedom there, and we have some pretty cool material options. And I'll give you an example of what we might do with some of the materials in a little bit. But sort of, a key thing here is, and I want to point out, there are some similarities. I'll give you a little bit of sort of kind of some thoughts on this hybrid machine. The similarities between machining and additive. In machining, we have roughing cycles. And so usually you're hogging out a lot of material. It's lower precision, rougher surface finish in the whole bit. And then we have a finish pass where you have a lower material removal rate, but you get a much higher precision. Same thing in general with additive manufacturing. If I have large material deposition rates, basically I have a much lower accuracy system. So here we're looking at a blown powder system. We have systems, and I'll show them you a little bit, that have laser wire, so laser welders on them, or even MIG welders where we put down 3-inch or 6-inch beads on them. So they're very crude in terms of the geometry, but we can put a lot of material down very fast. But again, these are going to be made of stacking up weld beads together. So these are just the different types of things that we would look at. So if we take a look at some of the hybrid operations, one of the really nice things, in particular, as we start to go to a 4 or 5 axis machine, is we can change the direction of gravity, if you will. You notice that on the propeller, and this is just a simple example where we're printing this L shape over here, and nominally you would need some sort of support below this blue structure, but we printed the blue part first in this orientation and then rotated it and printed the green part second. So you can do some very interesting things. In general, for our additive, we're either going to use a blown powder, which is typically about ½ pound per hour, but we get some pretty nice resolution there, or the wire feed, which is about an order of magnitude faster, but again, it's a rougher finish. But the beauty of it, I think, if you've used any of the powder systems, you've got to have respirators and special gloves and so forth to deal with the powder. Wire feed, I just go to MSC or to Lincoln Electric, order up my spool of wire and stick it in the machine, and I'm ready to go. So in terms of operations in a shop, this one is very easy to go with, as opposed to anything special going on with the blown powder. Even in terms of post-processing, a lot of times you've got to clean the powder out. Here, no powder to clean out. So again, people say, well, what's going to win? They each have their advantages, so it just depends on, it's like saying, what's the best machine tool? Is it a mill? Is it a lathe? Is it vertical? Is it horizontal? They each have their advantages. And then, of course, in subtractive, right now, we're just talking your standard machining. In terms of some of the lower costs, and this is a great example we get from a colleague, Professor Yamazaki out at Berkeley. He shows this part that's usually made out of machined Inconel. So I start out with a big Inconel tube, and I machine it all the way to get all these different features. What he has shown here is we start out with a material, 316 stainless substrate, and we just print the Inconel, and then we machine it to final shape. So now you're using much less Inconel, and you're having to machine a lot less Inconel. So 97% material cost reduction and significant reduction in terms of time and so forth. You know, saves you an awful lot of money as well. You know, 90,000 versus 2,500. So not too bad. So let's take a look at both. This is a wire machine, and so this is the Mazak. This is a 5-axis Mazak machine. And again, one of the things you have to be careful about is we have an additive head and a subtractive spindle. So you do lose this distance, actually twice this distance in terms of the machine capability, because the part's got to be able to reach under here and also reach under here. You know, I can't use the full travel of the machine because it can't get to both of these of the deposition and the machining part of at the same time. So you do lose some space when you put the when you put the additive head in there. But again, in this particular case, we made this propeller on here, no support structures and so forth, built it up where we didn't build it up from scratch. We started with a piece of bar stock. The other thing that I really do want to point out is people are familiar with constant surface speed on their machining operations. You have the same type of thing in the additive operations. So basically, constant surface speed is constant material removal rate. Here we have a constant material deposition rate. And that is really, we're feeding the wire out at a constant speed. And so what you can see, we're actually putting material down in a ball joint. So this is a ball socket for, I believe it's a hip implant. But you can see when you get to the apex of the sphere, you can see that this actually spins much faster because you've got to get a higher surface speed. Well, you've got to have a constant surface speed as you get to the apex of that sphere. So it's going to spin faster because we're putting down a constant amount of material. So lots of synergies between the two. The blown powder system that we show over here, this is the Okuma one. And what's really nice about this is this actually is more of it's also a mill turn machine. I think we can go up to about 800 RPM. So here you can actually see that we're building this, we'll call it a nose cone, if you will. It could just be a cup or a vase. But as we're building it, we're not going back and forth. We're just spinning it. So this is more of a cylindrical projection, but there is no start and stop here, so we can get continuous motion. And where we need to build the wall up, you can see we're rocking it back and forth to allow us to build it up. So you don't have to worry about the overhang structure there. You build some, you rock it in a little bit, and then you continue to build the thickness in terms of the wall. The other thing that's really cool about this one is here you're actually looking at the weld pool, and we're just starting to work on some controls areas in here, but you're looking down the core of the fiber optics, so we can actually see what's going on with the weld pool, which is really, it's very interesting. Now, there's a lot of, it's not just about the machine as well. We do a lot of work with Hypermill or with Autodesk and so forth. When you think about slicing on the 5-axis machine, so here we built this structure. This is just a hollow structure over here. This was done on the Mazak, but again, you can't slice it linearly. You have to slice it into chord fashion because you're really printing it in this chordal fashion. And when you print it up, and here I'm just showing it on the impeller, you can print it up. Again, no support structures, as you can see, because we're rotating as we're printing it. Now, the one thing I do want to highlight is that as you print this thing, clearly I've got less material that's got to come in over here. I can't just print a straight plane or a straight line over here. So as you can see here, when we blow up this area, we do have to do some modifications. So it's not just, okay, we're going to go off and use this, but we are actually going to do some modifications to your classical approaches. So these types of machines are really allowing us to do a whole lot more with our systems as we move along. But you've got to think a little bit more out of the box. The other thing that's really nice is you could imagine machining this thing. So as we machine this thing, it's going to ring like heck. One of the things that we might do, as opposed to for access, for example, it's hard to get a tool in here. We might actually do the machining ahead of time. So print some, then machine, print some more, then machine, so we can use smaller tooling. The other really nice thing about this is as you're machining, you might get some motion as you do some stress relieving, some residual stresses. If you machine here and you've got this very long part, you've got a lot of motion out here. On the other hand, we can machine on a stubby part. It might move a little bit, but then we can put down some more material. So we can work our way out and really avoid some of the motions that we see from some of the residual stresses. So one of the things we're looking at is just blade repair. So here we're actually looking at how do we repair the blade and how do we control that blade repair. I'm not going to get too much into this, but basically we can come in, we can measure, probe in the machine, probe the blade, remove the worn area, print on new material, and then machine. This is just a surrogate blade; it's not an actual blade. And then machine it to merge that material together, so we can actually repair the blade. And we're doing a lot of this work in conjunction with a number of our partners, Delta Tech Ops. Excuse me, Zeiss. Zeiss is doing a lot of our inspection and so forth. And we are using. And this actually is a video, and this is showing the information coming off of the machine. We are using information flowing out of the machine to understand what's going on with our particular part. And as we're making this part, we're actually recording information about what the machine is doing. So in fact, if I go to the next one here, and this is just the record for this particular part here, we understand exactly all of the settings on the machine. And so we can make sure that we're right at our 100%. And here we're taking a look at the feed rate override. So we've been making this part exactly at the design feed. Now, again, if you're thinking, well, on the machining side, a lot of times when people are running it, they might run it a little bit below. So a slower operation because they're afraid of the machining the first time around. This is really a bad thing when we're talking about additive. You really have to hit your target trajectories and velocities for additive to get the right part. And in fact, what you see over here is somebody has said, okay, well, we're machining, we're being a little bit cautious. Okay, now I'm going to crank it up. And I think we've all seen our operators operate at 120, 130, 140%. And so again, when we make a part, we can record all the machine parameters and make sure they're all within specifications. So we know when that part shows up, it'll show up with its digital passport. From a cyber secure perspective, it was made according to spec. This is not a counterfeit. It is original and it was made according to spec. So we can move this along. The other thing we can do is we can actually control. So now using our standard machine tool, so this is a hybrid machine tool, but we can actually control it using more advanced capabilities. Certainly we have in-machine probing, but we can also start to take a look at infrared cameras. And I'll show you what we're doing there in just a minute. But the idea really is to say, look, if the part gets too hot, that camera is going to tell an outside computer out in the cloud saying, hey, part is too hot, hold up on the machine. So we're now controlling the machine from the cloud. It's not a real-time, it's a pseudo real-time control. It's on a layer-by-layer basis, but the architecture is completely in place. The machines you buy today are capable of doing this in a secure fashion if you interface them correctly. So let me give you the example here. So in this particular case, we're just building a wall. It's a surrogate for a turbine blade. Here we're just going as fast as we can, just say put it down. But you can see that this overheats and it kind of bends over and kind of melts over and it's really a mess. What you're seeing over here is we're watching it. When the camera says the part is too hot, we're telling the machine to hold on for just a minute. And then when it's ready to make the next layer, when it cools down enough, then it makes the next layer. You can see here initially, of course, we're printing on a cool surface. So we're okay. We actually print fairly rapidly. And then over time, this heat builds up, and so it slows down the printing. And so you can actually see what the temperature looks like, and we make sure it does not go beyond a certain amount. We've actually taken...
Hey, Tom.
Yes.
We're running a little over, and I see you've got 22 total slides. Could we move this along a bit?
Yeah, sure. I was targeting this for a 30-minute presentation, but I can certainly bring
it on time. And we also want to address the issue of how do our research community interact with Oak Ridge National Labs.
Right. Okay. Well, that I think that's fine. And so one of the things that we have going on over here is and I'll just show you this last slide. And I think that this will probably be good enough in terms of where we really want to go. This last slide here, this last image here, basically what's happening is we're now probing the part. So we're actually taking a look at the part cooling, and so you can see this is just the typical cooling for the part, and we actually see it coming down, and so we know exactly when we're ready to, the stresses are at the right part and so forth, that we can move to the next level in terms of printing. The other thing that we can actually see is we have this information stored, so we know about the material characteristics and so forth, so we know that we have the right material, everything is correct in terms of the process. And so really where we're at, in fact, I think probably, probably where I'll go is we'll just go right to the last slide over here. And again, my apologies. I was timed for, and my timer here says we're at about 22 minutes, but no problem in terms of moving it forward. I want to point out a couple of things. So a lot of what we're talking about, people say, well, I'm going to lose my job because of automation. This is not true. What we are doing here, you still need an operator, you still need people in there. You are making life better. I testified in front of Congress, this was about 10 years ago. Congressman said, when am I going to get the robot to unload the dishwasher? The computer scientist next to me said, in about 10 years, we're still not that close. This is thousands, tens of thousands of dollars. This is a few $100s. They're not compatible, right? The person is still way better. People are excellent, and so they work together. So there also are the workforce development, but making sure that we integrate it into the workforce. So look, so here's my friend Medusa. So here are my 3 robots. They're working synchronously here together. Here they're working independently on the large turntable. But basically where we're at is, look, the digital thread is a two-way street. So how you're going to be working with this is data are going to be coming up. We're going to be analyzing processes, but we're also going to be supporting the workforce that's out there. In terms of working with us, really what happens is we're about identifying new technology. So if there's a new technology that you want to get out there, we're not going to do it on our own. We partner with industry. So you saw the Mazak machine. This is a Lincoln electric setup in terms of welding. So what we do, and we typically operate in a CRADA fashion. So in this particular case, Lincoln is putting in a certain amount of money, and the Department of Energy is matching it. The Department of Energy is funding us to do a lot of the work with Lincoln on this system. They bring in, I would say, about 80% of the technical know-how and capability for this project. We bring in about 20% of the materials and the control and the process modeling capability that really pushes us over the finish line. Really what we're about is we can de-risk the type of work that's going on. So companies will say, this is too much for us to take on. We partner with the companies, and that partnering can be bring in equipment. We'll use your equipment. We don't even want to own your equipment. We'll give it back to you in the end, but we can work on the depreciation schedule for that equipment. We have engineers from our partners. We have technicians from our partners in here working on this. And by the way, they're leveraging it. So for example, Zeiss is another partner. You saw that. So we'll print something on this system, and then we'll inspect it on our Zeiss tomography machines. It's good for Lincoln. It's good for Zeiss. It's good for everybody. So again, the idea is to scale technology as quickly as possible. We can do this in an open environment like the manufacturing demonstration facility. We can do it in an ITAR controlled space like our carbon fiber technology facility, or we can do it in a classified facility in a SCIF. And our whole approach is try and do it as much in the open as possible to try and keep our cost levels down. So again, the idea really is there's technology that is out there that you could use that's important to U.S. industry, whether again on the civilian side, or on the military side, important to U.S. industry that we scale it up. We're the place that you come to work on it. Now it's got to fit within our portfolio. I encourage you to go to our website. So all you have to do is look up Oak Ridge National Laboratory and Manufacturing Demonstration Facility, or Oak Ridge National Laboratory and Manufacturing. You'll see everything that's going on over here. If it fits in the portfolio, feel free to ping us. We've got a whole team that are working with individuals. We're not super concerned about intellectual property. We don't want the intellectual property. We want to give it to our partners. So those terms are very open. They're very generous. You got to pay a little bit because that's what the law says, but we're really not out. We're not trying to make funding ourselves and so forth, along those intellectual property lines. Anyways, I'll close with one of my favorite statements from one of my favorite 20th century philosophers, and it was certainly true in the 20th century, and it's very true today. In times of change, learners inherit the earth, while learned find themselves beautifully equipped to deal with a world that no longer exists. And that comes from Eric Hoffer. And the reality is technology is accelerating really quickly, and we are here to help that technology acceleration to get it into mainstream production. Thanks very much. Be very happy to answer any questions.
That was fantastic. So how does a research organization interact with INL?
Well, we're Oak Ridge National Laboratories, but I got to tell you, that's okay. Idaho National Laboratory is one of our partners, and so in fact, they may interact via our operations with Idaho National Laboratory, in particular on the cybersecurity side. But basically how we interact, I mean, just this morning, so Mazak, you saw that machine, we were sitting with their overall engineering and design team and taking a look at what do the next generation systems need to look like, and then we'll design it and we'll build it. And in fact, that next generation system is here. We'll even run, trial parts for potential customers and so forth. So again, we don't own that particular piece of equipment. So in fact, once we're done with it and we move on to the next project, maybe that customer will buy it right off of our floor and take it. So the idea is really working together and getting things moving. If you come out and visit, if you come in another 3 or 4 years, you will not see the same equipment on our floor because we are always moving into next generation technology.
So you're really commercializing the technology and then moving it out of the lab.
Well, we're working with our commercial partners, but we're making it commercially viable. So it's not just, yep, we're working on the technology, but what's the value proposition? What's the business proposition? So again, the hybrid machine, the beauty of it is, look, do you have enough business to justify this big 3D printer? Probably not initially, but look, it's also a machine tool. So you can use it as a 5-axis machine tool. Maybe you're only using it 10% of the time for additive, but while you build up that business, you can still use it as a machine tool. So, we start to take a look at a lot of the techno-economic analysis that's out there.
Well, thank you so much. Great presentation. Appreciate it. And I'm going to take you up on it. I'm going to come out and see your labs out there at Oak Ridge National Labs. Thank you.
So Linda, I know we're running a bit behind. We do have a question. Someone's raised their hand. Lee?
Okay.
Or Leah?
Okay, yeah. Tom, this is Andre Lee from Michigan State University. Beautiful talk.
Thank you.
How do you guys, I've seen some of these additive manufacturing that tend to be what I refer to as the traditional materials. Sort of metals or powders or ceramics and polymer powders. But when we start dealing with composite where that you have a continuous fiber, and how do you guys, any thought about in the sort of a manufacturing world that from your end, from an additive perspective, for continuous fiber reinforced composite as a reinforcement material system?
Yeah. So you saw the picture of the Cobra, the 3D printed car. There were actually we do have the capability, and these are on our BAMs, our big area additive manufacturing polymer, of putting down a continuous fiber strand into the feed. So we actually these are the input are pellets. So these are our extruders with augers and so forth on them. One of the other things that we have learned is you don't need the continuous fiber. I think. And pardon my English here, but I believe it's if you get to about 3 inches long, you do get the same benefits of the continuous fiber. But yes, on the polymer side, we can't extrude the continuous fiber. We haven't. We do have extrusion systems, again, polymer in our machine tools, but we haven't gone that far in the machine tool. So I think that there is a very good possibility there. Yep.
Thank you.
Yep.
Again, thank you very much. I'm sorry, we do have to move on. You have to give us back control of the screen.
Okay, let me and hang on 2 seconds. Just takes a second here to get out of this. Okay,
there we go.
Great.
Thank you. Thank you so much.
My pleasure.
To our next presentation, which is Idaho National Labs, another one of the national labs in the United States, and one that's close to Utah. So in many ways, we do feel that they're our national lab. And this is a pre-recorded session. So I'm going to turn the screen back over to Kathy, and she will run the video. Welcome back to the UMDC Defense Manufacturing Research Symposium. Our next speaker is from the Idaho National Labs. We are going to be talking about some of the programs that Idaho National Lab has in defense manufacturing, and also some ways that the Utah research institutions, academics, and companies can work and align with Idaho National Lab. In many ways, Utah considers INL our national lab because of the proximity. Rob O'Brien is going to be speaking with us today. Welcome, Rob. Thank you for joining us.
Thank you.
Fundamentally, Rob's research has focused on the development of processes and methodologies for advanced materials and in deploying these advanced materials and systems in extreme environments. So let me turn it over to you now, Rob. Why don't you share your screen? And we look forward to your presentation. I'll come back and we can ask some questions later.
Wonderful. Thank you. Well, it's a pleasure to be with everyone this afternoon. Again, to share our interest in advanced design and manufacturing for extreme environments. And also to give a background, a brief background on what Idaho National Lab's fundamental missions are and the mission areas that I think can be seen as opportunities for collaboration and connection to the broader industry base. So with that, I'd like to jump in to give that small overview of where Idaho National Lab sits and a little bit of background of how many employees we have, roughly 4,900 employees that cover a variety of roles and functions across a number of mission areas. We have 5 mission areas at INL that we'll talk about in just a moment. 5 mission areas at INL. Idaho National Lab can be seen geographically in the eastern Idaho Snake River Plain. We are roughly 890 square miles of what we would say is lab space. This is open land and facilities that allow us to perform very unique mission support functions for both the Department of Energy and our collaborators in a number of agencies and sectors. We have, if we think about business volume, we were in FY19, we were $1.35 billion business volume. And I think there's a lot of excitement in the energy sectors and a lot of opportunity for that business volume to grow along with our industry collaborators and partners. We have some statistics on the right-hand side. We have 4 operating statistics on the right-hand side. We have 4 operating statistics on the right-hand side. We have 4 operating statistics on the right-hand side. We have 4 operating statistics on the right-hand side. Years. We've been here as a lab for just over 70 years. There are 17.5 miles of railroad, 40 miles of primary roads within the complexes themselves. And a lot of opportunity with infrastructure for testing infrastructure. We have 7 substations and interfaces for power grid, and in addition, 112 miles of high voltage transmission lines. So this is certainly relevant for our interests in supporting cyber security awareness and testing of this infrastructure and critical infrastructure. As another note, we have our own support infrastructure, including fire and EMS. And we have 3 fire stations at the Idaho National Lab. So a lot of great capability and support infrastructure that can enable a number of mission areas R&D. Idaho National Lab is not a sole lab. As we know, we're one of 17 Department of Energy national laboratories that are nationwide. Idaho National Lab in blue here, we fundamentally serve nuclear energy. Idaho National Lab in blue here, we fundamentally national and homeland security mission. Nuclear energy. Idaho National Lab in blue here, some of those defense applications as well, and some opportunities later throughout this presentation where we perform research. But in general, the work that we do across the labs is interconnected. The programs the labs we support is interconnected. Bridge across many other the labs installation is interconnected. Bridge across whether it's is interconnected. Bridge the Oak Ridge National Lab in advanced manufacturing is the fundamental emphasis in this talk is focused, but also other energy applications that we explore together with other parts of the complex. So our fundamental mission at the Department of Energy National Labs is to support energy science, national security, and environmental stewardship. And the work that we do at INL is certainly no different. We support unique and multidisciplinary goals and science exploration that typically bridge beyond the scope of university and academic institutions, really to support research in both energy and national strategic priorities. Of course, tied to that is developing critical infrastructure and capabilities from a science and an energy perspective that really require government support, and the national labs help enable that sort of research. Within Idaho National Lab, we have some fundamental missions or primary mission areas. These are in nuclear science and technology, national and homeland security science and technology, and energy and environment science and technology. And the cross-cutting nature of some of the infrastructure that we have supports all of these mission areas, both the nuclear science and an energy environment, and then in addition the work that we do in national and homeland security in support of branches of the Department of Defense. If we think about advanced manufacturing, we see advanced design and manufacturing as an enabling approach to design and manufacturing as an enabling that serve both in harsh design and manufacturing as an enabling that enable that serve both in harsh design and manufacturing as an enabling also enable broader industry competitiveness both nationally and internationally. And the work that we're doing really focuses on the fundamental process discovery, and then accelerating the discovery and enabling refinement and ultimately leading to utilization and deployment in the industry sectors. We're looking at clean energy technologies, methods that reduce carbon, that allow competitiveness for industry, both from a sustainability perspective and economics perspective. We work in the areas of secure design manufacturing, enabling the conjunction between cyber awareness, cyber engineering, and sustained manufacturing. And the sectors that we look at are, of course, tied to our mission areas. So nuclear, energy, space, and defense are primary areas of interest. Examples of work areas that we do in advanced manufacturing. Examples of areas of additive manufacturing. We see additive manufacturing as a method for controlling feedstock, for controlling composite makeup of new advanced materials. We also look at the conjunction between methods like additive manufacturing and steps and processes that can finish a material or assemble a system. And so we include in that other efficient manufacturing methods, such as direct energy processing and electric field assisted sintering and joining methods as examples to access some of these materials for harsh environments. So our initiative was set up a little over 2 years ago to engage in advanced design and manufacturing for extreme environments, based on our interests areas and also the mission areas of the national labs. And so we established an initiative that is based on 3 pillars: process discovery, the initial discovery of a manufacturing method or material system. And then we have a second pillar that is focused on secure digital design and manufacturing. And our third pillar is based on intensification and scale-up, that is looking at tech transfer and enabling the utilization of the discoveries that are made in the early stages, utilizing the design methodologies that are developed, and then putting them to practice to enable competitive manufacturing processes. So within the initiative, of course, the 5 directorates that the lab has mission areas in. On the left-hand graphic are some examples of systems and components that we develop manufacturing technologies for. And around the outside, you'll see the areas of interest might be nuclear fuels, of course, focused on our nuclear science and technology interests, ballistic protective materials, hypersonic materials, and electronic systems are to note, and I think relevant to the defense interests. Within the pillars that you'll see in the central graphic on the outside, process discovery, secure digital design and manufacturing, and intensification and scale up, we also engage in, of course, subcategory activities that support those pillars. And each are equally important in terms of execution and manufacturing for harsh or extreme environments. Everything from proof of principle testing, so experimental interrogation, verification and validation of modeling and simulation methods. This is a very important step when we're developing materials from first principles or from theory. It is important to both perform verification of the models and then perform unique types of experimental interrogation of materials or manufacturing processes using in situ experimentation and instrumentation. That goes hand in hand with process-informed design, which is what we see as a methodology set to bridge between taking a design that is for a specific application and having a distilled or understood methodology for manufacturing a material, designing that part both to work within that process, but also modifying the process to make a microstructure, as an example, that is of interest or relevant to that design application. Cyber engineering goes hand in hand as we design manufacturing spaces, as we design the equipment and apparatus, as well as the overall design space, what would traditionally be bridged into an enterprise environment that could be gapped from the manufacturing environment. We see that cyber engineering is an essential part of our future in manufacturing. We see that there is a lot of opportunity both to develop approaches, but also to ensure product surety and ability to deliver on a mission by tying cyber engineering from first principles development. And that goes hand in hand with automation, plant design, pilot demonstrations, and of course, there is an element in digital twin tied with modeling and simulation to all of the discovery phases. So all of these items that we mention here are very much interconnected and play an essential role in our initiative. If we think about capabilities at INL, and then I'd like to also comment on how this touches the rest of the complex. We have some unique capabilities. The capabilities that have been developed and invested within INL stem from both programmatic interest and internal research and development efforts, such as IRAD-like or what we call lab-directed research and development projects and programs. The infrastructure that has been developed has certainly touched a broad number of areas that you'll see here in advanced manufacturing. And the infrastructure is not in one individual location. We actually have capabilities that are assisted both in radiological environments, so extreme environments from the nuclear science perspective, but also in the cold or secure environments, such as in the EES and TR Energy and Environment Science and Technology, or our National and Homeland Security sections. So we have a number of capabilities in additive or 3D printing that tie to nuclear fuel systems components. It ties to systems, thermal engineering components, thermal management systems, so there are some common sort of sistered capabilities there in additive manufacturing, both in our what we call our research and education campus, which is in the city of Idaho Falls, and then some 30 miles outside of the city at our materials and fuels complex. That is the MFC symbol that you see here with some of the purple capabilities. We look at materials and, of course, looking at how materials perform in extreme environments. We're interested in performance in nuclear reactors. So our advanced test reactor is a capability that we engage to test performance. At the advanced test reactor, we also have some manufacturing capabilities that support the primary mission there, which is enabling irradiation testing. Back at the materials and fuels complex, there are some capabilities to grow single crystal materials that are of interest in terms of understanding material performance, eliminating thermal transportation convolution or complications that we would see with polycrystalline materials of a new type of material. For example, trying to understand thermal conductivity can be challenging, especially with phonon scattering. And so using single crystal growth methods to grow materials of interest and then find the fundamental heat transfer properties, we can connect those back to our modeling and simulation capabilities. Over on the right-hand side of this graphic in yellow, you'll see the nuclear science and technology capabilities are very complementary. Moose is a box that, this is a modeling and simulation framework that has been developed over the last 10, 15 years at Idaho National Lab and is used throughout the DOE complex and within academia and industry partners to streamline simulation of complex physics. And there are a lot of capabilities there that are being developed for advanced manufacturing, a suite of tools that can probe and estimate the performance of a manufacturing approach. Equally, in pile instrumentation, as we talk about material performance in test, embedded sensors are essential. Embedded sensors that work within the manufacturing process, sensors that work within operation in a nuclear reactor and other extreme environments. So there are a lot of cross-cutting and complementary capabilities that you'll see here across the INL complex that really assist. Everything from material manufacturing, coatings, assembly, joining, and overall testing as systems or components. I think there's some very exciting capabilities that can be brought to bear on a whole number of very different problem sets. One area to note is our Center for Advanced Energy Studies, or CAES. This is, there are some unique capabilities there in microscopy that are more open access for academic institution partnering, and that includes everything from process chemistry, sample prep, and a microscopy suite with state-of-the-art instrumentation that is accessible to any institution that would like to participate. Mentioned the connectivity to the rest of the National Lab network. We work closely with colleagues across the National Lab complex, especially focused on advanced manufacturing. Our friends and colleagues at Oak Ridge National Lab, the manufacturing development facility, certainly have a lot of complementary research, especially in the additive advanced manufacturing realm, and certainly we have some very complementary work at INL. We partner with other parts of the complex to solve mission area challenges and manufacturing challenges. And we have collaborations with a number of other national labs, including Ames Lab, Lawrence Livermore, Kansas City plant, and NETL. And examples of those can be seen in the Critical Materials Institute and the Remade Institute. I'd like to talk a little bit more about our research and education campus and highlight some deeper connections and opportunities with capabilities. So our research and education campus has a fundamental role in advanced manufacturing. This is to enable advances in energy and harsh environment materials development by engaging in process discovery phase exploration of materials. That's coupled with modeling and simulation methods development, as well as utilization. And I like to call this distilling process science from discovery through intensification to deployment. So this is both the front and back end of the discovery phase. Some of the capabilities to talk a little bit more, I think these are areas for collaboration. Spark plasma sintering, we'll talk a little bit about that in a moment, but there's some very unique capabilities that spark plasma sintering or electric field assisted sintering can bring to manufacturing materials very rapidly and affordably. We have capabilities in trusted electronics and instrumentation manufacturing, being able to go from chip to finished electronic component in a secure environment is very attractive. And we'll give you an example towards the end of this presentation where this has been very useful most recently. We have capabilities in additive, as we mentioned, lens manufacturing, filament deposition methodologies, plasma jet, binder jet, and also digital light processing are methods that are being developed for a number of applications. Roll-to-roll, one of the challenges in production of hydrogen is being able to manufacture fuel cells that are efficient or electrolysis cells that are efficient, and roll-to-roll methodologies coupled with some of our additive and EFAST methods are certainly of great use and interest there. We have a number of capabilities in welding, laser welding, for example, and annealing, surface coatings to act as barriers for corrosion resistance. And then on the end of life side, we have a lot of work that is focused on e-waste recycle and polymer and metals recycle. Some examples of some of the in-pile instrumentation that we develop in embedded sensors might include systems like this. This is the micro-pocket fission detector that allows us to measure reactor power. And as you can see by the size of this compared to a penny on the right-hand side here, you can see that the stack of individual cells can give us a spectral analysis of reactor power, so both fast and thermal neutron spectrum. This is very useful for reactor engineering, but it does highlight the capability for microelectronic and microsensor development. At our materials and fuels complex, which I mentioned is some 30 miles outside of Idaho Falls, we see the function of advanced manufacturing here as bringing to the table a number of unique capabilities and very unique infrastructure that allows us to enable advances in nuclear fuel systems components. It allows us to develop irradiation science experiments and ultimately reactor technologies that are improved over the current state-of-the-art processes. And we do this by adapting and analyzing new or novel techniques for manufacturing. You'll see this, that the facilities are certainly in a remote location and house very unique both processing and controls, environmental and engineering controls, to allow a number of materials for extreme environments to be probed. Some examples of capabilities here again focus on electric field assisted sintering, radiation science development, manufacturing of experiments that go into reactors, and also other tests, including ballistic testing. Single crystal growth, we have a number of powder metallurgy techniques that are available for research, and then of course advanced coatings and more advanced joining and welding techniques. I did want to talk very quickly about electric field assisted sintering. We see this as a very exciting method that can support manufacturing materials for harsh environments. This is a technique that is akin to traditional hot press powder metallurgy techniques that can turn powders into solid compacts. And these compacts can be complex in geometry. They do not have to be right cylinder. They can be a number of different complex shapes, including curvature and internal facets that allow operation in the desired environment. This technique uses kiloamps of current, but for a very short amount of time to process material into a solid. It's typically performed at low voltage, some 20 volts or less of DC, but it is kiloamps per square centimeter in current density. It can be a continuous DC current that is applied to a powder inside an electrically conductive net shaping tool, or it can be a pulse DC current. So there are a number of approaches that give you an average temperature, but ultimately this technique is performed, it can be net shape, done in a much shorter amount of time, therefore saves an incredible amount of energy over traditional powder metallurgy techniques. And equally, the energy saving is felt because this process technique is performed at 40 to 50% of the melting point of the materials, as opposed to 80% of the melting point. So an incredible reduction in temperature can be achieved because of the nature of the electric field and its influence on sintering. Some examples of things that we've worked on and development of electric field assisted sintering at Idaho National Lab. We started some of our interest and research in spark plasma sintering in 2007. We had some internal research and development. This allowed us to develop infrastructure that you see on the bottom left side. It was a small electric field assisted sintering system, roughly 1500 amps of power supply, and relatively small hydraulic press. And then over the years, we've developed a number of other infrastructure and capabilities that enable EFAS development at different scales, more akin to bench scale production effort. So between 2011 to 2015, we developed a very unique capability that had an integrated glove box and one of these EFAS systems that could press not just inert materials, but also radiological materials. So we had all of the engineering controls in place to handle some harsh environment materials. And since then, this system has supported a number of industry partners and mission areas, including NASA, projects for Aerojet Rocketdyne, and other national and homeland security mission areas in both nuclear and reactive materials, and also hard ceramic materials. So incredible capabilities. Since then, we've deployed these systems at the Materials and Fuels Complex and grown capabilities in our research and education campus. Some examples include hard ceramic materials, complex net shapes in those, also thermoelectric materials for harnessing heat for energy recovery, advanced accident tolerant fuels, corrosion resistant materials, advanced isotope target, so isotope production target for medical applications, and then also some fuels and materials for ultra high temperature reactors. And what you'll see in the center of this picture is a stack of some fuels, and then the hexagonal shape that you see in the center with flow channels. This represents space reactor fuels that are of great interest for enabling exploration and national security missions of the future. Some examples of where that work has been irradiated. In 2019, we performed the first irradiation of advanced manufactured nuclear fuels inside an additively manufactured capsule at our treat reactor that had just come online just a few months prior. This was a reactor built in the 1950s and was mothballed in 1994. We recovered that system in 2018, and in June of 2019, we made this world first attempt to irradiate, and these fuels have been tested at 3000 Kelvin, and they're relevant to some of the advanced space reactor systems. As we think about growth and where next, when we talk about industrial deployment and utilization, we are in the process of finalizing construction, the world's largest true electric field assisted sintering system. This is an 800-ton press, 150,000 amp current system capable of sintering 24 to 36 inch diameter components and stacks of materials to net shape, or to join and diffusion bond very complex, hard to join materials. This includes a number of materials for our national and homeland security mission areas, including super hard, ultra incompressible materials, transparent materials, and ceramics. Again, in the nuclear fuels area, looking at mass production of nuclear fuel systems, components, and materials that are very difficult to manufacture using traditional methodologies. There are interests in supercapacitor, solid state energy storage, and heat exchange technologies, as well as solid oxide electrolysis cell technologies for hydrogen production and fuel cell operation. This system is now in the final throes of completion of its installation. This picture is dated from October. It's not quite complete in this picture, but you get a sense of the scale with some of our staff here stood to the right-hand side of this piece of infrastructure. We performed the first power tests in the system on the 8th of March this year. So it's very much a process and system that is nearing completion. But this will be an established backbone for automation controls, a test bed for cyber engineering. It will allow us to test a number of materials that are relevant to both the defense and energy sectors, as well as other industry areas as well. I did want to highlight some of our support in the under the CARES Act and to highlight the cross-cutting capabilities at Idaho National Lab, and ability to adapt to new problem sets and new challenges. As we've all been facing with the COVID-19 pandemic, there is a lot of challenges in the both the supply chain, but also in sustainability and also resilience in manufacturing. And we have demonstrated a number of approaches to continue operations, but we've also supported broader industry sectors that Idaho National Lab had not traditionally supported, specifically in the medical manufacturing areas, in collaboration with a total of 16 labs focused on the National Virtual Biotechnology Lab. And Idaho National Lab has led 6 laboratories in developing novel ventilation techniques and transformative ventilation technologies that can support the medical sector and patients recovering from COVID-19. In doing so, we've developed a number of low cost, affordable, and non-competitive for supply chain components, ventilators that could be deployed world over. Our colleagues at Lawrence Livermore National Lab had an emergency use agreement and spun out a product through an industry partner that is now taken to an international market. We have supported an Idaho company from Coeur d'Alene, Idaho, Percussion Air, in modernizing electronics and manufacturing approaches to allow mass production of some of their technologies in what is known as intrapulmonary percussive ventilation, which has had a number of use cases, including in DoD missions, both nationally and internationally, for life flight and field hospital ventilation. We've looked at transformative sources of oxygen generation to eliminate the supply chain, using air to concentrate, using additive manufacturing to concentrate air into pure oxygen or purify the oxygen for feeding ventilators. In addition, we've supported an Oak Ridge National Lab led effort in a collaboration that is developing PPE or respiratory PPE technologies, including standing up testing capabilities that are in accordance with the NIOSH standards to allow us to rapidly screen candidate materials for filters. And additionally, INL has supported in data analytics activities to look at supply chain and connecting that to virology modeling to allow us to predict where the needs are going to arise for system deployment, and also looking at supply chain gaps and being able to support industry in closing those gaps. So in summary, Idaho National Lab has a lot of interesting manufacturing capabilities that can support a broad industry base, including defense and energy sectors. It's fair to say that we have a high consequence, critical path supply chain and component manufacturing set of activities and challenges. And these are certainly analogous to sort of broad industrial and defense activities. We have existing advanced digital design and manufacturing capabilities that can be exercised to address a number of supply chain challenges and problem sets, both for DOE, can be used for DoD, NNSA, and other industrial commercial needs in research and development. We believe that cyber-informed design and secure manufacturing is going to be essential at every step and in every installation for industrial and commercial activities. And the capabilities and the collaborations that we have to offer, both from an expertise and infrastructure perspective, can be leveraged for a number of potential projects and programs, and we can be seen as a test bed under the AMO Cybersecurity Institute, the CyMani, that was recently awarded, but other work for others and strategic partnership projects are also possible to be engaged in these frontiers. So with that, I'd really like to thank everybody for the time, and certainly my contact information is here at the bottom available, and would be very happy to connect you with our colleagues across the lab if there's areas of interest that you would like to discuss offline, and also happy to field other questions as they arise. So thanks again for the time, and enjoy the rest of the session. Thank you.
Thank you so much, Rob. What a great presentation. It was comprehensive, yet very much focused on the Utah defense manufacturing community. Which brings me to, so how does INL seek out or find academic and other research institutions like those of ours here in Utah to partner with?
We certainly are positioned to respond, to answer questions and solve problems collaboratively. Our doors are open and certainly receptive at any time to field those questions and areas of interest. We often see opportunity through both the Department of Energy and other areas for partnering. So with funding opportunity announcements that are through the DOE exchange websites or other branches of federal government funding opportunities that we can partner with. We also have the ability to partner to solve immediate problems that may fall outside of those funding opportunities through our strategic partnerships projects and work for others or creative processes.
And you may not know this, but one of the major focuses for Utah Defense Manufacturing Community programs is workforce. And part of workforce is apprenticeships and internships. Does INL have that kind of a program for internships or apprenticeships?
Absolutely. We have an annual and an ongoing internship program. Can be at any point throughout the calendar year. We actively encourage partnership with academia and encourage students to come participate in internship programs that typically run through the summer. Although examples include longer term internships for placement of graduate students at the National Lab capabilities to engage in exercising work that is in support of their PhD or master's theses. So there's a lot of opportunity there from that respect. But we equally value the talent pipeline. Solving the energy challenges cannot be done by building infrastructure. It's a combination of growing expertise and the capabilities together. And so we're very much interested in collaborating and growing that talent pipeline together, both with industry and academia.
Yeah, and the students certainly come at these problems with a very different perspective that is refreshing and can present new and unique opportunities. Well, thank you very much. The UDMC will follow up directly with INL and see if we can establish a formal relationship for some of these programs. Well, again, thank you, Rob. I appreciate your time, and thank you for your contributions to today's symposium. Well, welcome back after this has been a long day, I know, but we certainly have covered an awful lot of fantastic information. Our next speaker is Dr. Thomas Lockhart, and Utah is so fortunate to have Tom here at the Hill Air Force Base and part of our community, given his deep background and his expertise. He is currently he's a member of the Senior Executive Service. He's Director of Engineering and Technical Management, Air Force Nuclear Weapons Center, Hill Air Force Base. He enhances the warfighter support as the center's lead for nuclear systems and digital development technology and insertion, and multi-domain systems support for the Minuteman III and the launch of the cruise missile and command and control. And prior to coming back here to Utah to run this nuclear weapons center, he was a director with the Air Force Research Lab. So that's why you've heard his name several times today as someone who was a leader, a thought leader within AFRL. So Tom, I know that you're on, so welcome. And I've got your slides here. And let me put it into presentation mode, and I'll let you take it away.
Well, thank you for the opportunity to present today, and I really do. Can you hear me okay, first of all?
Yes, we hear you fine.
Perfect. Okay. I thought Crystal got in here earlier and set it up. Just to give you insight, what I was doing is I was meeting with the Secretary. The Secretary of the Air Force was out visiting Hill Air Force Base. So I thank you for letting me go last. Hopefully it'll cap, I think Dr. Russell will be after me, but it'll kind of cap the day with some really good information. So Utah Advanced Materials and Manufacturing Initiative is a very important to the Air and Space Force here at Utah. And so my presentation or my talk today is really about this digital research, innovation to support air and space. And it really kind of focuses in on system thinking and digital engineering and several of the areas that we've matured over time in the Air Force and now the Space Force. For anybody that hasn't met me, I'm Tom Lockhart. I am the Director of Engineering for the Nuke Weapons Center, but I'm also the Senior Functional out at Hill Air Force Base. And so that picture that you see on the chart itself is an aerial view of Hill Air Force Base. And just to give you kind of the size and the scope of work that's actually done there, we've got about 25,000 people plus, and we have over 4,000 scientists, engineers, and technical support staff that work at the base itself. And it's a broad range of experience, all the way from research in basic and applied, into acquisition, buying products, and sustaining and supply chain management. And it covers A-10s, old, they call them the warthogs, but old aircraft, F-16, all the way to the newest generations of F-22, F-35, and space and radars. So if you think about that, that is a very, very large portfolio, economic impacts of billions of dollars across the northern part of Utah. So let's go to the next chart. With every government presentation we have to, or military presentation, we usually put in, an overview. And really today, what I'd like to do is cover a little bit about Utah and some of the connective tissues that already exist with the base, and kind of run from north to south, and just areas that I see that are already doing innovative research. I'd be amiss if I didn't talk a little bit about our portfolio on the Air Force Nuclear Weapons Center. And why I want to do that is just show you why it's a big impact to Utah today and into the future. And then the last little takeaway from the overview is I really want to touch on 8 areas that I believe this group is enabling the future of the Air and Space Force. Okay, it looks like we already moved forward. And so why Utah? Why is Utah so important? And so I'm going to start in the northern tip of the state and in Cache Valley. If you get up there, Logan, you've got Utah State University, a real good partner with us in education and outreach. But they also have a group that's a university affiliated research center, and it's Space Dynamics Lab. And if you look at the work they're doing, they're leading a lot of the air and space research in small satellites and small, kind of commercial type entities. And so that's right in Cache Valley. So if you go over to the left, Box Elder and Tooele, we've got Utah Test and Training Range that's out there, Army Depot. And so there's a lot of really great work and ability to go out and look at the materials and the manufacturing and actually test this. It's the largest contiguous running test range in the United States. So it runs all the way from Utah through Nevada to California. So that's very important. If you go into Weber State University, and they've been just a great partner. I talked about 25,000 people, 4,000 engineers. They've been just a phenomenal partner as we kind of build out, legacy aircraft, legacy spacecraft, also radars and so forth. But they've been an invaluable partner. And so now getting into Salt Lake with the new airport, if you actually go down there, there's a lot of big businesses as you kind of trickle down by the airport, Harris, but both Salt Lake Community College and University of Utah have been really great working composites, additive manufacturing, and really some of the tough questions that we've got to deal with in the materials manufacturing. And I call it the physics-based modeling. And so hopefully Dr. Bunning, Ms. Timothychik, and then probably Dr. Russell after I get done, they'll talk about the importance of integrated computational materials science and engineering and how those things work together and how do we understand that in order for us to ensure, in our case, aircraft airworthiness, and the nuclear side, nuke surety, to make sure it's the level that we expect it to. Down past Salt Lake into and on, if you actually, we call it the Silicon Slopes. And it's just a whole bunch of software and software development capabilities. I think Adobe's there, Dell, etc. And it really is now this digital ecosystem that I'm going to talk about. And it really is so important to have this in order for us to generate this innovative, novel way of doing materials and manufacturing. And so the two bullets on here, Utah business infrastructure, you think about the airport and what's been done there and the advancement of that airport is really important. The corridors across the state, I-15, I-80, they're advancing on ramps, off ramps. So we have the business infrastructure. And then the really thing that I'm going to push a little bit today is this Utah digital network. We're becoming a digital state, and it's very important for the work that this group is actually undertaking because it really is advanced materials and manufacturing, and you really have to have the ability to understand that. And this digital network actually provides it to us. Okay, next chart. The next chart that's coming up, so the Air Force Nuclear Weapon System Center and these are the systems, and I've highlighted in kind of orange, Utah is critical for our success. And so I'll start on the left-hand side. Utah has been an invaluable partner for us for a long time, and it's been on what's called Minuteman III. And on the far left, it says W78, W87. That's just nomenclature in the Air Force for the weapon itself. And that's the air vehicle equipment. They call it the flight system. As you kind of migrate to the middle, it's more than just the air vehicle equipment. It's launch facilities, launch control centers, transportation and handling. We have a whole fleet of trucks that we actually have to move components to and from the various bases in Wyoming, in Montana, and North Dakota. And so we've got that. And then across the top is how do you actually command and control and communicate with those various locations. And then on the right-hand side, it talks about weapons and aircraft interface. So Utah, 2/3 of the nuclear triad is really somewhat maintained here in Utah. And you think throughout these different weapon systems that I just hit, the materials that have to be understood, the manufacturing process that have to be consistent, and we've got it all the way throughout this portfolio. And I've identified our large ACAT, which is acquisition category ones, which are multi-billion-dollar programs, ground-based strategic deterrent. It's very large, and it's a replacement program for the Minuteman III. And then on the right-hand side, you've got highlighted some aircraft that are actually maintained here, so they're outlined. And then in the middle in the purple shows some of the weapons themselves. Gravity weapons, B-61-12 is a tail kit assembly. It's a gravity weapon. And then air launch cruise missile is another weapon. And we've got a big program called long range standoff weapons that's actually replacing the air launch cruise missile. But this is all important for Utah because there is materials work that needs to be done in these areas. If you just look at Minuteman on the far left, that air vehicle equipment, composite casings, right? Engine nozzle ducts that are actually metals, specialized components that have to be additively manufactured. Those are all things that would be considered as part of this Materials and Manufacturing Institute. So let's go to the next chart. So I thought this was really important. I hope Dr. Bunning talked a little bit about that, but where is the Air Force today and where does it need to go into the future? And that's both air and space. And where does this Utah Advanced Manufacturing Materials really play? In the top, it says National Defense Strategy, National Security Innovation Base. And so we need to make sure we're postured correctly, that we can kind of take care of the weapon systems. And if you start, that's actually a timeline back to World War I, and the Wright Flyer is really the first aircraft where it was balsa wood and fabric that was actually being done. And how do we actually make that thing fly? And then over time, you see these peaks and valleys where we generated a lot of different. So right after World War I, we had a lot of activities on advancing aircraft. And then between wars, it kind of slowed down. Then World War II, it happened that we had a lot more aircraft that we had to maintain and different capabilities. So we had fighters, we had bombers, we had cargo, and all needed different material composition. The faster you fly, the different types of materials you actually needed. And then you kind of go into the Cold War era where we had, like ICBMs and missiles and Missile Defense Agency. And then for the last few years, it has actually kind of narrowed down. And so we had limited numbers, limited quantities, but it is changing. And so we're trying to figure out how to ensure that we keep up and keep a competitive edge with a near peer or a peer adversaries. That National Defense Strategy and National Security Innovation Base kind of shows you those peaks and valleys over time, which is really important. And here's the 8 items that I just hope you kind of take away from my presentation of areas that we're interested in and important for materials and manufacturing. The first, and I'm sure you've heard it throughout the day, is additive. We've designed things in the past with subtractive manufacturing process. We set up for the industrial age and we did big manufacturing. Today, it's unique. Things are changing. And so the 2 pictures I have in there, one is just an item where it shows different material orientation and different material composition and how you can put that together. The second one, that dome that's kind of silver, shows you that we're starting to blend as part of additive functional materials, so things that are smart, with structural materials and coming up with different compositions. And so that's interesting. And with the research side of the house, and hopefully Dr. Russell and Dr. Bunning talked about it, getting to the point where electronics, now you have the ability to use materials and manufacturing that are actually flexible. So they can actually move back and forth like flexible electronics instead of having a hard case computer. Wouldn't it be nice to have that component linked into your actual jacket and actually keep control of it on your jacket itself? That's one. I'll work the alternate navigations. So most of the time you get up in the morning, if you're going to drive to work, you're going to drive across the state, you grab your phone, you plug in a MapQuest or Google Maps where you want to go, and you kind of run the course. And it's all linked in with our current satellites, our GPS, our global positioning system, and it gives you that information as you kind of move across. Well, what happens when that's not available? And so can you actually figure out different signals or opportunity that you can actually augment that and put together in such a way that you actually know where you're going and you didn't have to have satellite connection all the time, every time. And so we're looking at materials for positioning, navigation, and timing. And so there's new compositions in all 3 of those areas that we need to pay attention to. And in the future, there's a lot of conversations about quantum. And in my mind, quantum, people jump to quantum computing. You know, how do we make computers go faster? I think quantum's really novel in this area. So position, navigation, and timing, quantum sensing, quantum encryption, et cetera. So I think that's interesting, an area that really needs that additional work. Network capabilities. So just talked about, you know, kind of manufacturing process and some new novel ideas on navigation. But now with these new networks, and I didn't say this, but I probably should have, is University of Utah is the 5G network hub, and they're trying to do a smart city. But we're getting new network capabilities. And so we can share things with the cloud, connectivity, and high bandwidth, things that we hadn't done before in the past. And I think that's really important for the materials community, because we did have a materials genome edition defining the materials, but we didn't have the network or the infrastructure to communicate those with this you know, crowdsourced environment. And so now we're getting to the point where we have the connectivity and the data that we can actually put together, and I'll call it crowdsourcing, but the ability to kind of use whoever the subject matter expert is in that specific area to go work on those elements. And this one also just in network, the optics side of the house, new materials, dense wave, dual multiplexing, the ability to kind of communicate back and forth across the network, really some novel ideas there, et cetera. Many targets and layers that we actually have to kind of go after and understand. And networks and spectrum management, I think there was some questions about cyber and cybersecurity. Obviously, as we aggregate, get to the cloud, connect things together, worldwide coverage, we've got to pay attention to that. And so some of the things that we can manipulate and understand on the lower end is really important for us in that network and spectrum management side of the house, waveform protections, et cetera. I'm going to jump down to the far left hand side, and it really is on the space. If you've been watching, there's a lot of commercial space activities today. Web One, SpaceX. I think I've seen articles that have gone upwards to 2,000 to 3,000 satellites. And I mentioned the Space Dynamics Lab that's up there at Utah State. Very interesting kind of dynamics. One of the leaders in these smaller CubeSat type activities. And how do you put a lot of them out up there quickly? But I think we're just at the forefront of understanding the abilities in commercial space. So it'd be great. You have, you know, let's say 3,000 satellites up there, all staring down at the Earth. Think about what you could actually see around the world, what's happening, news, and et cetera. Communication, it would be like an internet in the sky, the ability to go across from one of these satellites to the next. So I think there's a lot. And then really the design aspects for this materials and manufacturing. Think about structural materials with smart materials in there, like a battery that's actually printed into a satellite. Open standards, the ability to make changes over time for satellites. A lot of times we thought we'd launch, we leave it, and then eventually it'll come back in, burn itself out, and it's done. But now, what about logistics? Could we actually go up there and change out solar cells? Could we actually refuel, et cetera? And a logistics arm to actually do that. And so I think space, and part of the reason I wanted to give this presentation, I think there's a lot of areas in the materials and manufacturing side of the house that really we can target to help out our space community today. Getting into the smaller scale, the nanotechnology and energetics, as you kind of manipulate carbon nanotubes, carbon nanofibers, first of all, in the United States, we really need to be able to do better on carbon nanofibers. I think a lot of our carbon nanofibers are actually being imported from a company in Toray, Japan. And so we've got to get better on how to produce that and actually utilize it. But it's actually with carbon nanotubes and carbon nanofibers, the ability to manipulate those things in a different manner. And it's really interesting to kind of see what we can actually do there. I did put energetics also at that scale. Oops, this app may be dangerous. You know, no. Okay, I've stopped there. Okay. I saw a note. Hopefully I didn't lose you guys. Is everybody good? Belinda, still good?
Yeah, we're fine. I don't know what you saw. We just see your presentation.
Okay. It pushed me up, said, this is dangerous. Do not do anything. And so I stopped right there. Okay. Let me finish up with energetics. The ability to manipulate things at the lower scale. You have, the ability to make it burn fast or burn slow, depending on how you orient the energetics itself. Human performance, we've really got to now take that understanding at the lower level and be able to bring it up. And for the Air Force at the mission campaign, what happens when you use a different material composition at the physics level? What happens at the mission campaign? And we're linking things together. And so really, in the past, because of our networks, our capabilities to kind of link those physics-based models into the mission campaign, it didn't exist. And now we're starting to get there. And that's where I introduced that integrated computational materials science and engineering ability. And to get off the kind of stage here is we're moving into an era where digital engineering has the ability to go up and down the chain, depending on what the customer needs are. And so the next couple charts is really where I've been pushing the Air Force and the Space Force to kind of move into it. And we call it digital engineering. It really model-based system engineering, the ability to actually look at different, if you're a material scientist, a mechanical engineer, establish those relationships, change data, understand data, and put it up to the level and visualize it at the mission campaign. In our case, it'd be like an aircraft flying in a certain area of the world, the spacecraft, orbiting the Earth, and making sure we understand that. So let's go to the next chart. So this digital side of the house, we've been in the Air Force doing acquisitions the same almost since the 90s. We've changed a few things, but it really has significantly changed here in the last, year, 2 years, because of the capability the cloud has actually provided and the network that I've been talking about. And so I'm going to just kind of walk you through this. I call it integrated digital ecosystems, milestones, and processes. So when you see MS, that's a milestone. And what we use for terminology, so milestone A, if you're thinking about research, it's usually at the basic and applied level. And then when we get to milestone B, if you're actually starting to build something into an application, and then when you get to milestone C, you're actually getting into productionizing it and manufacturing. So just to kind of level set what the terminology here, but it's a digital ecosystem, cloud enabled, with this model based system engineering, the ability to model things and capture the product over its life cycle and perform analytics. So you think about most of our products today, at least on the phones and stuff like that, they're designed for about 24 to 48 months. And you've got to actually understand that length of time. And in the past, with an aircraft, we just automatically defaulted to 20 years, 20,000 miles. Now we're trying to figure out low cost, attritable type items. And so we've got to understand the model based tools, that's the middle, and the capture, the environment, and the life cycle of the system. And so we go from understanding the basic and applied research, showing what it actually can perform to. Now, when we go out to you industry and our academic partners, is really start providing what is called a higher level architecture, but they call it model-based system engineering, system architecture. So we're providing those types of higher level architectures so you can actually build to. And then so once you get into production, you're actually starting to capture data as you manufacture. So manufacturing, you have tolerance bands. And so the materials may be right at the edge. So the first time that it gets over 20,000 miles, it's going to fail. Or in other cases, you've over-designed it so it could have lasted 30,000 miles. And so we capture that manufacturing data and understand that, so we can actually predict the life when it's been used in these environments. And so the milestone C, system development and production, into system life, we actually capture that data. Leaving it open with MBSC, you have open standards. So over time, this is probably going to change. The customer will want something different. And you have the ability to kind of put into the model those changes and have a supply chain that actually can provide those different materials and manufactured components. So, okay, that's kind of system lifecycle, and hopefully you get an idea. This is where we're going from an Air Force perspective, is this integrated digital ecosystem, cloud enabled, with the ability to do modeling up front to understand it, capture the data over the life, and be able to do the analysis and visualization at any level. You could have a pilot understanding all the way down to a scientist. Okay, next chart. And this is my last one is how do this integrated digital environment tools play nicely together? And so you can actually start doing that, material composition all the way through product design into sustainment. And so I put this model in the middle. I really think it is the heartbeat. It really starts tying together disparate functions like electrical, mechanical, materials, and that kind of stuff, but it captures that architecture. So you really have the bone structure of what needs to be produced. And we're starting to build those out. We're starting to train our system engineers to understand how to put together this government reference architecture. Also, how do you validate and verify those disparate type relationships? That middle section is model-based system engineering and the ability to put the model together and relate those different functions together. Then we branch off to actually see on the right-hand side, it says operational analysis. So you built the architecture, you want to see how it executes over time. And so from a material standpoint, you kind of understand materials decay at a certain rate. Composites are actually a step function. It looks good for a long duration, and then all of a sudden it breaks and it has a problem. But with metals, you can kind of see over time. So operationally, how well it can actually perform with slight degradation all the way till disruption where something actually occurs. Behavioral models and algorithms, so we can actually calculate those things and get prognostics and predictive algorithms to actually understand that. The trade space, so we could actually see, maybe we want to leave this open. We recognize that there may be a change in technology, maybe that we're going to actually have to replace it anyway and bring it in for maintenance. So we need to kind of pay attention to that. But it's that trade space analysis in the performance itself. You don't want to interrupt the customer from doing its day-to-day job, but you want to also ensure that it's kept current and understood. The product lifecycle is the modeling, and then you capture that all the way from the top level system down to the materials, the physics based, and so you can actually link those together. Software, we recognize all these tools today don't really nicely play together, but they're out on the cloud, and so we're putting the middleware together to actually figure out how to take portions. The physics-based model usually run on a high-performance computing system, and you probably just want results to actually present to the system guys, and so you don't want the whole model in their actual MBSE tool. And so we're putting this software middleware together for the analysis and linkage up and down, and for, I call it authoritative data, the ability to understand what was actually provided, because at some point with aircraft, you have to certify, qualify, and there's a type certificate, and you have to be able to convince the airworthiness authorities it actually works. And that allows us to kind of connect the models with some of those more detailed physics-based tools. And then obviously, anytime you're dealing with manufacturing and materials, you've got to have cost trades. Hey, we may want to last longer, we want to last less because they're going to bring it in for change of oil and tires, brakes, and that kind of stuff. Or do you want to make it last longer and then charge more? And so that's the cost analysis. And then the last little piece is just tracing to the original requirements. But this is all what we're talking about in this integrated computational material science and engineering all the way up the chain. And then the last little piece, the blue box around all of this is the ability to take this out of our standard way of looking at things and being able to visualize it. And you have to really relate to the human on that one, the human eye. So augmented reality, virtual reality to kind of bring that up. Okay, I think that's my last chart. Sorry, it took me a little longer. I got interrupted there. So we'll just go to questions. Let's go ahead and go up one and we'll just go to questions. Is there anything that anybody would like to ask?
Thank you, Tom. That was a fabulous overview. Really appreciate your insights and providing such a comprehensive view. Yeah, so let's throw it out to questions and let me see if I can stop sharing my screen. There we go.
So Linda, it was only supposed to take 20 minutes, so I apologize. I went along. Sorry
Not
about that.
a problem. Obviously, that's been an issue today, which is why we're in the time where we are. With all of this good information, somebody's got to have a question.
Sorry, no questions in chat so far.
Well, I hate to let you off the hook like this because getting time with you is always so valuable. But it appears that we've worn everyone out through the day, and we do have one more presentation with John Russell. So, hey, thank you. Thank you for making time in your day. I appreciate your coming in, and even though you had such a busy day with the secretary and still joining us. Thank you so much, Tom.
Thank you, and good luck. I really do appreciate the invitation, and look forward to any partnering relationships in the future here at Hill.
Fantastic. Okay, so let me just switch. Go back to sorry, folks, give me a second here. There we go. Okay. So our last presentation is pre-recorded by John Russell, who's part of AFRL. And we asked him to help the novices like me on this symposium understand what everyone's been talking about all day today. And as he said, making sense of the acronym soup. He's done a fabulous job here. As I said, this is pre-recorded, so we won't be able to ask questions. And then I'll just do a quick wrap up. It's also short. It only runs 15 minutes. So I am going to stop sharing and turn it over to Kathy to run the video that we pre-recorded with John Russell. Thank you, everyone, for joining us today. It's been a long day, and you've heard a lot about the various DoD programs and the lead for each one of these specific areas. We're going to wrap up today's session with a great presentation by John Russell that'll help you navigate the alphabet soup of acronyms in putting together your proposals and understanding what is going on if you want to put in a proposal to the U.S. Air Force Research Lab. Dr. Russell has joined us today. He is the chief of the Air Force Research Laboratory's Structure and Technology Branch. And in this role, he is the senior manager of a team that develops and transitions new airframe structure technology for safety and efficiency in future Air Force weapons system. To do this, he builds partnerships with customers across the Air Force, across DoD, other government agencies, industry, and academia. In addition, he's one of the leading experts on composite materials. Dr. Russell has a doctor in science degree in chemical engineering from Washington University in St. Louis, and he is also a fellow of SME, the Society of Advanced Materials and Process Engineering, SAMPE, and with the Air Force Research Laboratory. So with this, let me turn over to you, John, to put your presentation up and share your wisdom that you've gathered.
All right, thank you, Talinda. And thanks to everybody for being on the talk today. I appreciate being able to talk to you. Let me pull up my slides here. All right, and before I go forward, Talinda, can you confirm that you have full screen?
Yeah, we've got the full screen and we hear you very well.
Great, thanks. All right, so good afternoon, everybody. As Talinda said, my name is John Russell, and I'm here to talk to you really not about the technology side of things, but about the language of DoD, making sense of the acronym soup, the language of the DoD and what it means for science and technology. So it's a long path from a technology concept to getting your technology on an airplane and then full supply chain integration. In between these two endpoints lies proof of concept, benchtop demonstration, characterization and testing, proof of system integration, pilot scale, and then advanced manufacturing, and then eventual adoption into the full supply chain. Each step in this process requires increasingly complex participation by technical support, business development, sales, marketing, production, accounting, and so forth. But navigating that path to technology transition is difficult enough. On top of that, the Air Force has its own particular language in describing everything, including funding, acquisition, and technical maturation. You might have heard of some of these terms and acronyms before, things like color of money, RDT&E, O&M, TEs, CIIs, DoD 5000, TRL, and MRL. Now, these are likely going to have you saying WTF at the end of the day. Now, many people don't understand how the system works in general when they don't understand the language as well. So the purpose of today's discussion is to define all these terms for the S&T community so that you can have a better understanding of how you can work with us. So I'll go through all of these one by one, well, other than WTF, because you know that one. And then we'll talk about the definition and the importance of each term. So color of money. So this does not refer to the Tom Cruise movie. This does not refer to Monopoly. Color of money is about different appropriations from Congress to run the Air Force. An appropriation is a fund set aside by Congress permitting federal agencies to incur obligations and to make payments out of the Treasury for specified purposes. So within the Air Force, there are two overarching types of appropriations. There's investments and then operations and maintenance. Each appropriation is designated by a 4-digit numeric identifier for the Treasury Department to use in execution tracking. And you can see all those numbers listed here on this chart. But the important one to know about for S&T is 3600 for RDT&E for the Air Force. So that's where all of our S&T comes out of. So next is RDT&E funding. So we'll drill down into that. So in particular, you are going to want to know about 6.1 through 6.3. That's the science and technology budget. So 6.1 is basic research, and it's about far-sighted, high payoff research that provides the basis for technological progress. It's about increasing fundamental knowledge and understanding. This is really mostly used to work with universities. The next step up the ladder of maturation is the 6.2 applied research funding. So things that graduate out of basic research flow into applied research, where you try to take a look at solutions for broadly defined military needs. And these efforts really establish an initial feasibility and practicality of proposed solutions. The next step up in maturity is 6.3 advanced technology development. This is where you start to work development of subsystems and components and things that really take a look at simulated environments for what the military needs. Projects in this category have a direct relevance to identified military needs. And just to round it out, just so you're aware, 6.4, 6.5, and 6.7 are really about taking the technology developed out of S&P and trying to apply them into a weapon system to meet current or near-term operational need. Then 6.6 is about R&D, RDT&E management and support work. So the next, drilling down a little further more into RDT&E are program elements. So program elements are a code within a budget category that represent a specific military capability or support activity. Congress designates how to spend funds within each color of money through the program elements. What I'm showing here in this table is an example of the 2020 defense appropriation for the Air Force for its basic research line and part of applied research. So you can see program elements for basic research sciences, university research initiatives, high energy lasers, et cetera. Now, oftentimes you may see here the amount in the final bill that's passed by Congress and signed by the president is different than the president's initial budget request. A program element could increase or decrease from the president's initial request based upon Congress's view of the area. So a companion to that term then is congressional interest items, or CII. You probably know these better as congressional ads or earmarks or pork. These are provisions inserted into appropriation bills that direct funds to a specific recipient while circumventing the merit-based or competitive funds allocation process. So this table here shows the 2020 appropriation for the Air Force's 6.3 funds for the Manufacturing Technology Program. As you can see here, Congress inserted several ads into this program element. Now, how these come about is typically an organization, such as a company, university, nonprofit, work with their representative or senator to include an earmark in a program element. Now, an important disclaimer, executive branch employees, such as myself, we cannot work with Congress to insert CIIs into the budget. That is a big no-no. We support the president's budget. However, if you plan on inserting an earmark into somebody's program element, let those people in the executive branch know that it's coming. It's really better for everybody so that there's no surprises. And it really improves the quality of the work that's going to be done with that CII funding. So next, let's move on to the DoD 5000. These regulations describe the DoD's acquisition process. They provide the policies and principles that govern the defense acquisition system and that form the management foundation for all DoD programs. And they identify the specific statutory and regulatory reports and other information requirements for each milestone review and decision point. So to put this in context around something you may have heard of, the F-35, Boeing, McDonnell Douglas, and Lockheed Martin were awarded contracts for material solution analyses. Then at milestone A, the DoD down selected to Boeing and Lockheed to move into the next phase, technology maturation and risk reduction. During this phase, both Lockheed and Boeing built and flew demonstrator aircraft. Then at milestone B, the government down selected to Lockheed Martin to go into engineering and manufacturing development, or EMD. And then finally at milestone C, Lockheed was awarded a contract for low rate initial production. So let's switch gears a little bit and talk about tech maturation. I'm sure many of you have heard the term TRLs, or technology readiness levels. These talk about the level of maturity of a technology relevant to its use in an application. These have been around for a long time now, and you can see they start from TRL 1, basic principles observed, going all the way up through TRL 9, so proven in an operational environment. So TRLs provide a common language to assess performance maturity of a technology and its plans for future maturation. And it really helps you understand the risk in trying to transition the technology to a weapons system application. So in general, if you tie these back to funding and funding types, so 6.1 basic research usually funds TRLs 1 and 2. The 6.2 applied research funds things that are generally TRL 3 and 4. And then 6.3 funds things that are TRL 5 and 6 to mature things up the ladder. The one thing about TRLs, though, is that questions still remain. So these talk about individual technology demonstrations, but what if you need more than one item? What if you need to build a whole production run? Is the level of performance of your demonstration going to be reproducible? Do you know what these things are going to cost once they're in full production? Can you make these things with the average run-of-the-mill factory worker rather than a host of PhDs? And finally, do you have the key materials and components available for a full production run? So to address these, we take a look at the manufacturing readiness levels. These were developed in the mid-2000s to answer those questions on the previous chart. MRLs are assessed to define the current level of manufacturing maturity, identify shortfalls and associated risk and cost. and then provide the basis for a plan for manufacturing maturation and risk management. And it's important to note that manufacturing readiness assessments are now a mandatory part of the source selection process in major acquisition programs. In addition, they're used also in R&D programs as we try to mature manufacturing along with the technology at the same time. Now, as we look at manufacturing readiness levels, it's not just one overall number. There's a number of things we need to take a look at to make sure that we know the manufacturing maturity level or manufacturing readiness level. So we take a look at the technology and its industrial base. Are the designs mature? Do you really have an understanding of your costs and your funding sources? Do you know what materials you're going to use? Do you have the process controls available? Do you have a quality management plan in place, including a plan for your suppliers? Is your workforce prepared to understand this technology when it gets into production? Do you have the facilities and the capital equipment available? And finally, do you have a manufacturing management plan? So just to wrap up, I hope you found this talk useful. It helps to make sense of the acronym soup that defines the DoD from its major weapon systems down to the S&T community. So I've defined some of these key terms of importance for the S&T community so that you have a better understanding of how you can work with us. I look forward to working with all of you soon. Thank you very much.
Thank you so much. That was fabulous. It definitely clarifies for all of our participants in this webinar on how to proceed, how to figure out what the language is that's being spoken. I guess I have one question, which is one that you and I have talked about a lot, and that is, I see you are the lead on composites. So could we talk a little bit about composites research at DoD?
Sure.
How do you see, I guess it's really with AFRL, the composites research programs proceeding, and what kinds of programs are you interested in?
So we run the gamut from developing new materials and processes to developing manufacturing processes to developing designs for the use of composites and systems. And even though we're separated in 3 different organizations, we all work together very well to try to move this forward. We're constantly looking at developing new materials for things like bringing 3D printing into composites. We're always looking for materials that have better properties in terms of strength and stiffness, as well as temperature capability. For manufacturing, we're trying to take a look at how do you bring the Industry 4.0 environment into composites. Composites has been pretty analog, and how do you take advantage of some of these new technologies like augmented reality, like digital asset tracking, and things of that nature to move the ball forward there. And for designs, what's the next step in terms of large integrated and bonded structures to make designs close for future aircraft concepts? We're going to need to improve the way that we do bonding in aircraft structures. And then finally, this whole concept of attritable structures. So airplanes with designed specifically for limited life from the get-go. We may be able to use designs and materials and manufacturing that typically aren't used in aerospace to try to take advantage of the relaxed requirements for airworthiness and airframe structural integrity that we anticipate are going to happen.
Excellent. That's a great answer. Thank you so much. And John, we really appreciate your taking the time to present and very good information. And we are your perfect wrap-up speaker for us. Well, thank you, everyone. It's been an incredible day. Let me just share a couple of things with you. First of all, thank you to all of our speakers. We all have learned a lot today, and I'm sure it's hard to write notes and you're wondering, can I get a copy of the presentations? All the proceedings, we're going to do proceedings from this day today, and they will be posted with the videos on the UMDC website, and that's the, oops, I could go, sorry, there we go. On the UMDC website, and that's the brand new, this is the first time we're really rolling it out. It's not 100% finished, but we are able to, that's how we were able to run the YouTube, was through the UtahDefenseManufacturing.org. We really have to big shout out and thank you to the Office of Local Defense and Community Cooperation, formerly Office of Economic Adjustment, for their leadership in putting this program in place. And we're the first year. There is funding for FY 2021 and consideration for FY 2022. So hopefully the funding will keep coming through as we do good things like we've just done today to move the ball forward for the warfighter and our industrial base. And also we have a big shout out to the Office of the Governor's Office of Economic Development, who put the proposal in and won the grant. And finally, in this continuing program for Utah Defense Manufacturing Community, look forward to having 2 additional symposiums this year, one on defense manufacturing workforce issues, and the second is on defense manufacturing supply chain issues. So with that, I thank you. I thank Kathy Bloomquist for all she's done to put this together, and Grow Utah, Justin Bott, has just done an awesome job in figuring out how to get all this technology to work, and our brand new Director of Marketing, Dustin Cedarholm, for working with us on putting this fabulous event together. So with that, we will conclude. Thank you, everyone.